All right, I think we can start. Yeah, so welcome to the first workshop on human object reconstruction. Really excited to have this workshop, and we're really happy to have like a great line of speakers. As you know, many people couldn't come, but we have people here in Zoom. And I want to just give you an overview of what's the talks that are coming, and also like give you a bit of background on the challenge that was organized. Yeah, so this is the list of organizers, and in particular, Shi Wang was the main person. So she did almost all the organization work. Unfortunately, she couldn't come because of visa issues. But yeah, she took responsibility for most of the workshop. So we had like reviewers. This is the technical committee that reviewed the papers that were submitted to the workshop. So thanks a lot to the people here. So just a little bit about the challenge. So the challenge was on reconstructing humans and objects, and we had 3 different tracks because we know the community is like working on this problem like separately. Hopefully, like it will be every time like more an integrated research problem. But basically, we had 3 tracks. One is human reconstruction, the other one is 6-degree freedom post-estimation, and then finally joint reconstruction of humans and objects. And the benchmark data set that we used is the Behave data set, which is a paper that came at CVPR 22, and it features like 3D humans jointly with 3D objects and the RGB video and the depth data of Kinect. And yeah, when we collected this data set, we designed an algorithm to make sure that the objects and the humans are accurate, and it's also annotated with contacts. So we're quite happy with the participation in the challenge. So we had 3 tracks, and overall we had more than 100 participants and more than 300 submissions. This was delayed. And so basically we had 75 participants and more than 150 submissions for the human reconstruction, 32 participants and more than 90 submissions for the 6-degree of freedom pose. And for the joint reconstruction, we had 35 participants with more than 60 submissions. So you can see that there's still like more people, and I think this also reflects like how many people are working in each of these fields. There's more people working on these problems in isolation, but hopefully we'll see more and more of this tackling this problem like jointly. So the winner of each track will be awarded with $500, which is a gift that was enabled by Adobe. So thanks to Adobe for this. And so this is the program. We'll have like Joseph Sivic first giving a talk, then Torsten Zadler, then we'll have like the challenge winners presentations. The poster session, unfortunately, this is the same for all the workshops, will be at the other building, right? Is this correct, right? So all the posters for all the workshops are in the other building, so it's a little bit inconvenient, but I think we'll manage. Then we'll have Kristen Grauman, Siyu Tang, and Ted Adelson, and finally we will like have time for the accepted papers. All right. Basically, yeah, without further ado, it's a great pleasure to have Joseph Sivic here, who is a professor at the Czech Institute of Technology, but he's also affiliated with INRIA, and he's also leading the Alice unit in Prague. And I mean, basically, he won lots of awards in many different areas of computer vision. We're really happy to have you here, and yeah, looking forward to your talk.
Thank you very much for the invitation and introduction. Let me set up here.
Yeah.
If I can get on the...
So now, yes, we will put this here. You have water?
And it works.
Yeah, it works. Perfect. It's just
Okay, right. So thank you very much again for the invitation and nice introduction. I will talk about today about learning person-object interactions from instructional video. So first I will, and we've done quite a lot of work in this area, and I will first show you what is an instructional video. If I, oh, here we can go. I mean, if you probably have seen this, but if you haven't, so this is an instructional video. There is someone, this person here is showing how to make yourself how to achieve a certain quite complex task. In this case, it's changing car tire. So he's showing how to interact with the different tools here to achieve the sequence of steps to remove the tire and exchange with another one. And what's interesting, he's talking about it in natural language while he's doing that. And if you don't like the one particular example of the video, there are actually many for the different, using different, on the internet, using different tools or different car types. And in fact, there are millions of instructional videos online for different domains, from car repair to cooking, gardening or health. So this really provides this outstanding repository of natural language and visual data about how people interact with the different objects and the world. And so what we would like to do is, given all this data, to extract some kind of an instructional manual for a specific task like changing car tire. And why would it be interesting? Well, imagine that you could then upload that instruction manual to a device like augmented reality device and give instruction to a novice user to do the task in a new environment or in a factory. You can imagine in manufacturing to guide new workers how to do things or check if there are things correct. So these are actually real use cases which people I would like to address, or you can upload this kind of instructions to a robot and perform this task in a different environment. So these are the kind of motivations which we have. And what I will do in this talk, I will survey some of our recent work in this area. And so here are some of the paper citations. And so when looking at this, it's going to be a progression from starting at the beginning from the top, from models which have very little physical grounding, which are just visual language models. So we will talk, you will see kind of different representations of person-object interactions, from just associations of visual appearance and language at the very top, through more complex physics-based representations, including, say, interaction forces, and then later using those representations to transfer some of these motions or interactions to robots. So you will see kind of this progression of different representation of a person-object interactions, what it could mean, and what we can do with it. Now I'm hoping I will get through all of this. So starting with the visual language representations at the very top, so very little physical or geometric representations. We've been working in this area. I will do kind of a quick intro. For a while, just the first thing was even given an instructional video or a set of instructional videos to extract the specific steps of changing car tire, which are here on the side, and localizing them in time. So this is, you see at the bottom, the ground truth and the predicted occurrences. And this was fine and interesting, but really this was just using 50 videos. So we were thinking, well, can we scale this up, this type of a learning, to much larger scale? And we created this data set by looking at WikiHow, where you can really find almost how to do anything. But we built this data set using the website and to collect sort of more than 20,000 different tasks, which are visual. So not how to fall in love, but how to make an ice cream, for example. We would download YouTube videos for those, more than 1 million videos, and chop them into short clips, where each of these clips would have a visual appearance, maybe 5-10 seconds, together with the narration, what the person is talking, what they say, what they show in the video. So we have more than 100 million of these short clips with narration, often showing some kind of an interaction of the person and the environment. And this is really one of the, and now there are sort of even larger data set, but I think this is still probably one of the largest focused on instructional videos. And this is just a comparison to existing data sets which are often manually annotated. So we have a data set which is 3 orders of magnitude bigger, but obtained sort of automatically using the automatic ASR, automatic transcription of the spoken language into the transcription. So, and how this works is that we would train a model which consists typically of some kind of a language network, language module, and a visual module, which are trained jointly, and they are trained to predict. And I will try to use the mouse if I don't want to will not hear me. And so we would have these visual appearance together with the narration, and those which are corresponding videos, they would be close in that space, and those which are from different videos would be found. And I will not go much into detail, but show just an example what one can use that for. What you can get here is you can then search the videos using natural language, and this is or even videos which do not have any language representation. You can make on glue and you will find videos when someone is gluing. You can tell this is interaction of a person object glue wood. You will find videos when someone is gluing wood. You can type cut wood and you will find videos someone cutting wood. And you can gradually more you can really the label space is very large because it's used by language, and you can find in more you can put together in complex queries like cut paper in a circle, and you will find videos of people cutting paper in a circle. So this really sort of avoids the need of manual annotations or lots of data, but using the natural language as often is done in images and also in videos, even instructional videos, to really have this very large language space. And what's interesting is also result a little bit now 2 years back, but I still like to show it how so on the x-axis is the number of training videos, on the y-axis is performance, higher is better. This is natural language based task on one particular data set. You can see that more data you do better on the task. I will not go into details what is this, and you can have a similar trend for several different data sets. You may recognize the different names. Often they will depict different types of videos, including instructional that people interact with objects. And what's interesting, the horizontal line is the performance obtained by training on the data from the object, from the specific data set manually provided. You can see that if you have enough noisy data, you can outperform the original method. So the original results from using the manually provided data. So this is really, showing how from this large scale noisy data set you can obtain interesting results. And I'll just do one more task. Again, this is sort of not explicit person-object interactions, say in the geometry, but still natural language. This is video question answering. This is another task that can measure performance of these video language models. And typically, this is an example what type of material is the man touching. So you have some sort of notion, you can recognize the interaction, but there is no geometric representation or what animal is shown as a cutout. This is a single frame from a video. So there is a video, this is a chosen frame. So you have to have a video representation. This frame was chosen so that you can see the interaction in a still image. And this is an example of output of these different models, the ground truth, and how examples of answers, what these models can do. And just to show you as a sort of teaser, how in this work we did it. So the model is essentially a transformer-based model where the input is a triplet of video question and answer, and using a contrastive loss, the model is trained on example training triplets. So this is a fairly straightforward, in a way, supervised training, but what's interesting how we obtain these triplets, that we really take this large-scale instructional data set, the how to 100 million, and convert this data set. It doesn't have video, it doesn't have the training data in the form of videos, questions and answers. It's just these natural language descriptions, but we use language, just pure language-based tools to convert the language into the triplets, and then obtain a very large scale. We call this data set SQA 69 million, because we have 69 million of person of these triplets of video question and answer. We can just train this model, this noisy data, and obtain, and here are some of the example results. So you can see what kind of, again, this is what is in the blue plate, and the answer is butter here. And or what is the man cutting is an example of person-object interaction here, and the model recognizes correctly it's a pipe. So it has a certain level of understanding what's happening, what the person is doing in the video, although without explicitly representing it. And just show you one of the latest results. One can also formulate this problem in a zero-shot manner and take a large-scale pre-trained image model, which is in this case CLIP. This is the visual backbone here in blue, together with a large-scale language model, which is also pre-trained and frozen. In this case, it's not autoregressive, it's a bidirectional language model, and fine-tune it using adaptation layers with very little parameters, and in a way not requiring huge training data in the form of just video with the line language, and fine-tune these two models together. So what's interesting on this figure that all these blue parts are frozen. So the original model, which has so larger, I'll show later how many parameters, a lot of it is frozen. You just fine-tune those adaptation layers, which are shown in pink, and obtain interesting results. And this is comparison on different data sets. It's small for some of you. Each column is a different data set. The first column is number of parameters, comparison with different methods. And the original model is close to 1 billion parameters. If you fine-tune everything, it turns out it doesn't work very well if you fine-tune everything. But if you just fine-tune using these adaptation layers, you can get very good performance on this data. And what's interesting is that this is one of the data sets, which is the first column. Even the latest results of GPT-4 have been published on this task. You can find them on the website, and it turns out, so this is the performance. So overall, it's still, even though it looks that this video language problem should be solved by a large extent now, we see that the overall performance is still not very, very good, 63%. So these are many of the questions which a 10-year-old would answer easily. Yet, 6 out of 10 or 4 out of 10, the models they are not getting correctly. So we still have quite a long way to go here. And the latest GPT-4 model is doing even worse. It's even getting 4 or 5 of the questions incorrectly out of 10 on average. So here are some of the examples of video language training, so without explicit models of person-object interactions. And I will now progress more towards models which are really targeted, trying to explicitly model person-object interactions. This is an example of work where we wish to sort of learn how people change the states of objects. An object, you can have this is sort of a notion from human perception. An object can have a state, which here could be an example, is a cup empty or full. And the person can change the state of the object by, say, in this case, pouring coffee into the cup, making the cup from empty to full. So this is an example of how these changes of object states from videos. This is also a few years back, and I will show our latest work in this direction. And here we have 3 different videos in rows, and the first column is the localized empty cup. In the middle is the pouring action, and on the right is the full cup, where the state has been changed in the video. So here is an example of the latest work where we like to learn how people change the states of objects while interacting with them automatically from the data. So the input to the method is just a set of, in this case, mainly instructional videos obtained from YouTube again. And they are obtained using queries like how to cut a pineapple, for example, or how to fold a paper plate. So this is a sort of pre-curated set of queries, and this is in some sense the only human input where we select around 50 of these sentences which say how people change state of an object, fold a paper plate, or cut an apple. And then we obtain for each of those about 1,000 videos from YouTube. And again, this is a noisy set of videos. And from this data, we would like to learn a model which would localize the states of the objects, like here the whole apple, then the cut apple, these are the two states, and the cutting action. And what's interesting, we like to do that without any supervision. So just in some kind of a self-supervised manner. So what we formulate is a set of constraints on this problem. And the key constraint is what we call the causal ordering constraint, that we would like that the initial state is first, then there is the cutting action, which is changing the state of the object, and then finally is the end state. So we would like to use this constraint, together with other constraints that I'll show later, as the only form of supervision for this problem. So no manual labeling, but using just those constraints to learn how from these videos to localize these different states. And why is this interesting? Well, one of the examples is using as a reward functions for robotics, for example. This is a very nice work from the team of Peter Fox, that they're using a video, well, in this case, they are so really learning policies or controllers for cutting specifically. There are kind of injury controls for that. But in our case, we'd like to use the video demonstration as some kind of a reward function for this task. And it's of course difficult because there's a huge visual variability for this, I think, inflating balloon. The videos are long and they have lots of unrelated content. So these are examples of videos which have 12 minutes, and then the states are, at very different locations. And finally, it's a very noisy set because it's got downloaded from YouTube. So you would have, if you fake cutting apple, you would have videos which do have cutting apple, but also videos like cutting other objects like branches of trees, or even cutting real iPhones. So it's a very noisy data set. So we'd like to have a method which can deal with that. So we designed this method, and there are sort of two main contributions here. Once we formulate a set of constraints which will form this self-supervision for this task. The key is the causal ordering constraint, and like this ordering of initial state, action, and end state. But together with additional constraints between and I will not go through all the details, it's in the paper, which sort of use, say, for example, the localized action as a negative for the object, and this turns out to be important. So we formulate a set of constraints with about 5 or 6, taking advantage of the structure of the problem, and like to localize, the ordering, and then how we can use the localized examples as negatives for the other tasks and the tasks between each other. And then it's sort of formulated as a self-supervised learning problem without any manual annotation. The second, we look at different architectures which could exploit how, in this case, the different tasks, in this case, cutting apple and cutting pineapple, can be learned together and so most leverage the information that there are, say, related actions or related objects. And we investigate different architectures for this problem experimentally. Spoiler is this one performs the best at the bottom, which really uses kind of 2 separate classifiers, one for objects, one for actions, and has a specific architectural laws for this. So we have this specific data set just for this, as I described, around 50 actions. It's more than 2,600 hours of videos, and we manually label only a small set for evaluation. The rest is unlabeled for training. And here are some of the examples. They are a little bit small here, but this is different actions like tortilla wrapping. This is initial state, the action, and the end state. T-shirt dyeing or paper plane folding are some examples on our data set. We've done this on different data sets. You might know the coin data set of instructional videos. And what's interesting, we can also learn on our data set, say how to cut avocado, and then transfer in a zero-shot manner to egocentric data sets. I think there will be a talk by Kristen Grauman later on egocentric data. And what's interesting, we show in the paper, we can learn on instructional videos, which are typically third person or egocentric often, and transfer to egocentric data sets and localize the different object states and actions in egocentric data. I will skip the evaluation, just maybe one sentence. It's interesting, you can get quite a bit by fine-tuning for the specific task. So when we take the whole architecture, even the backbone, and fine-tune for this problem of object states, I guess it's a little bit like fine-grained recognition. It's really to distinguish between these different states of objects. It helps if you find you. So we observe quite a boost in performance if we use, and we have enough data once we do it for all the tasks together, and using the multitask architecture and fine-tune the backbone for this problem. So, and I will, so running a little bit out of time, so I only got through the video language part, so I will zoom through a little bit by taking some of the highlights here. And in these problems, we have more geometric-based representations, and I will try to also say some of the lessons learned here. Here is an example of work where we input videos on the left, again, instructional video, and on the right is the estimated reconstruction of the motion. This is by the stick skeletal of the person, together with the tool, which is represented here only also as a stick, and together with the estimates of the interaction forces, which are here shown as yellow arrows, also the moments as white arrows, between the object and the ground and the person, between the person and the ground and the person and the tool. These, in the estimation, let me show this video, sorry. So this video again, really in the estimations format is an optimization problem based on 2D measurements from the data. And really these, and the estimates of the person object forces and the dynamics, and it acts as a sort of regularizer for this problem. That's what it's really doing. It's not a magic bullet, it sort of regularizes the problem in some physically plausible way. So here are some more examples. For this, we do it for 5 different tasks of people interacting with these stick-like tools. That's the main limitations of the approach. That is limited to these stick-like tools, and I will show we can try to alleviate that limitation in a more recent work. And so I will sort of start moving more quickly, so within time. In this work, so we saw our main motivation is to extract these person-object interactions in this detailed manner. But can we then transfer the motion to a robot? And so this is an example of a work where on the left is the input video from YouTube, and on the right is the motion, this shoveling motion transferred onto the robot. And it's hard because it's a very dynamic motion. It's hard to learn this without the demonstration. And how this works is that we take the trajectory on the bottom left, which is the extracted 3D motion, and then align the simulation, and automatically have a method to align a simulation environment with a sparse reward with mainly the tool motion in this case. And then we can perform the initialization from the video, we can perform reinforcement learning in the simulated environment, and learn a controller, in this case, the open loop controller, which can be transferred on a real robot from this. So it's really using the person-object interaction extracted from the video automatically to learn a policy controller on the robot. And so we have several, so 3 different interaction types of interaction with the shovel, in this case, a hammer and a scythe. We have 5 videos from internet, from YouTube. We have testing environment, which we built for these 3 different tasks, for hammer, for shoveling, and for the scythe. And then we can evaluate how well we can train so this is transferred from each video independently. I will skipping some of the details of the evaluation. It's in the paper, but we can show we can do this transfer reasonably well. But what's interesting is that this whole approach is sort of robot agnostic, and this is the reason is that we actually don't use the human motion at all, which was kind of an interesting insight. We only focus and transfer the motion of the tool. We do need the human to extract the motion of the tool, because without that, getting the hammer out of the video would be too hard. But once we have the trajectory of the tool, this is what we use to guide the learning process. So we don't care about the morphology of the human once we have the tool motion or the robot, and we can just use the same algorithm for several different robots with different morphology. Going from a 7D of Panda, 6D of UR5, or even 11D of Freedom Talos robot. And the same algorithm is just used out of the box for each of these robots to learn a different controller transferring material. And we are hoping to really actually do transfer it on a real Talos. This is a real humanoid robot, and our collaborators in labs in Toulouse. It's not easy to do experiment with this because, as you said, you can see it has to be mounted on a sort of these safeguard rails. But eventually, we'd like to go into together with our colleagues to show some of these dynamic motions on real robots in this environment. And finally, I will try to go super quick here. We will have maybe one question or so, or two questions. We've put a lot of effort into also estimating the 6D pose of objects from video. So we have this method which can, given a known CAD model, we have to have a known CAD model. We can then estimate the pose of the different objects here. In this case, it's because you can manipulate them and can do other things. This is our examples from the Bob challenge where we haven't run on this challenge. We still plan to do it, but we haven't got around to doing that. But I think the data is very interesting. We just need to get a student to do it. So that these are results from the Bob challenge already a couple of years back, and we extended it also to articulated objects. But I will show you. This is estimating not only the 6D pose but also the articulation of the robot together. So it's the same approach, render and compare. So you render a large data set of robots in different articulations and estimate 6D pose and articulation together. And the latest instantiation which we have, it's called, we call the method Megapose, which just published in Coral in November or December last year. And what in the previous work, you need to know the objects, the CAD models before you train the model. Now we train a single model with a large synthetic data set. So you can see that all synthetic images. It's, I think, 2 million images, 50,000 different objects on top of each other. And we pre-train this model on this data. And then you can, at test time, you still need to know the CAD model of the object. Oops. Like a cub here, but you can, it's okay. You still need to know the CAD model of the object, but you don't need to see the training. So for any new objects, you have the CAD model, you can apply the method and get 6D pose quite accurately. So there is this pre-training stage, and then at test time, you have a new CAD model, and you can estimate the pose of the object. And what it allows you, and it works because the training can have occlusions, it works with occlusions. And at test time, then it allows us, and this is kind of another sort of detailed representation of person-object interaction, to solve what we call the tunnel problem, which was inspired by the roboticist we work with in Paris. So the goal is to put this object through this big tunnel. This is just kind of a mock-up case. It's a hard problem because you have to change the graph. So you have to sort of start here, then we put the object and then regraph it from the other side. So for doing the task and motion planning for this is not easy because the need for the regraphs. And but for us, because we can use the human demonstration. So what we have here as input are actually these 6D poses of objects together with the estimated of contacts, interactions. These are the boxes for this use excellent method of David Fuhi's student. And with this, we can really prime this is a standard RRP planner, but we can use the estimated object poses and contacts to really solve this task and motion planning task and transfer it on the robot. And I will finish here with this result. And I thank you very much for your attention. Thank you.
Yeah, thanks, Joseph, for this exciting talk. We have time for questions. You can send out and use the microphone.
Yeah. Hi, my question is about the third part of the work that you discussed. So when you're transferring motion to a robot, then you are learning it in simulation. So what kind of reward are you using for training? For example, like let's say the task is scooping some sand or some material. So the main application that I'm concerned is that I should be able to scoop a large volume or something, right? So if you're training with that kind of objective in simulation, then do you also get similar kind of scooping performance in the real world or not?
Yeah, so it's a very good question. So actually, each of these environments, they have their own sparse reward, which is really exactly the number of or amount of material which you transfer. It turns out that doing RL with this sparse reward is almost impossible. I mean, it's, you could be running for a long time and never got any sensible result. So just this sparse reward doesn't work at all. You could engineer a reward which kind of goes like a proximity of the tool to the objects. And our student, because when we submitted the review, says, well, what if you engineer the reward as you normally roboticists would do for every single task? They would engineer the reward. So she did it. She spent a few days on this for every task. She managed to engineer it to get reasonable results. But we showed that we can do it only with the sparse reward and the guidance from the video. So the video gives you initialization, which is close enough. Which so then you get a policy which is not, and I'm not showing it, but which is not very good, but it transports few balls already. And from that initialization and using only the sparse reward, you can learn then a nice and smooth policy.
There's one follow-up as well. So, do you also see a positive correlation in the amount of material scooped in the simulation and in the real world or not?
We do at the same time. Of course, the material in the real world is slightly different. This example. So how we, and this is kind of ongoing work in progress, what we use is domain randomization. What's very important is to get the first policy, but once you have a first successful policy in the environment, you can do this gradual domain randomization and you change the parameters, even placement of the objects or the weight of the material or the properties of the material. As long as you change this gradually, you can still learn more robust and more and more robust policy. But you have to start from something, from an initial policy. So I think that's the direction which we do. Once you have the first policy from the demonstration, expand its kind of a scope by domain randomization for across different materials. But we have a little bit of this in the paper at the end, but we haven't quite explored this fully. But I think this is one possible direction of going.
Thank you.
Hi, great talks. I had a question, like a general question on what do you think about use of other modalities, say vision derived or sensors for parsing instructional videos, like say pose, depth, or maybe sensors like gaze and so on.
So I mean, so there is on a large scale, the instruction videos we typically just have the video, but language now and audio, and of course these are useful modalities. I think once you start scaling up to real sort of robotic environments, you start getting more sensors. And there is also nice work when people collect data on robotic platforms. And you start getting back things like depth, for example, or, and I think that will like to have a very nice talk on getting like haptic feedback. And I think all of this data will be, whenever we introduce, my experience, whenever we introduce a modality, the results just get better because you kind of have additional source of information. So I think I'm looking forward to get more data with different modalities, and I think that it will just be better. We'll have interesting.
But again, so that's with new sensors, but what about vision derived modality, like just say optical, flow or 2D pose, 3D pose from videos?
Well, so 3D pose, I think that's one thing why we are putting a lot of effort, because we think that just having pixels in, and who knows, I think this we have to see, and there will be different, different methods. But we think that the more information you get out of the scene, like the 6D pose estimator, which we have now with the megapose, we do think it will give us more information about the input scene, and we think that the learner will be easier. We still have to show it. But that's the direction which we're exploring now. We start trying to connect large language models to give us planning capabilities, but with more structured scene representations, which will have some notion of what the objects are and what are their poses, at least for the ones which So that's the direction which we're going. But I think the time will tell what will work there.
Yeah, thanks.
When I'm watching how-to videos for my own use, I find that the ones that are most useful are the ones that show you all the things that can go wrong, in addition to the one that show you exactly how it will go if everything goes according to plan. The way to interpret that is what you're doing.
It's a great question. I think we typically be quoted as a limitation of this whole approach is that people, most of them, they don't have the failure cases. So you have just examples of things which are correct. I think it's interesting. We haven't, and now we've got me thinking maybe we should really try to look for those which do have some of the failure examples. That's kind of really enrich the additional information with negative data. The way we were thinking about it is to really complement with this simulation. And then once we, like, as we, the example which I've shown, which was a step in that direction, because in the simulation, yes, we have the successful example from the instructional videos, but the simulator can kind of explore some of the other paths which are, which would be the failures. But I think trying to extract explicit failures from instructions, I think is a great idea. Look into this. Thank you.
Yeah, so I have a question about, so the first, I mean, it's kind of a very, it's gonna be a hard question to answer, but I wanna know what is your view on this. So in the first part of the talk, I see that language plays a very important role. And the second part of the talk, basically you're not using language at all. So do you think that language could be useful for this more fine grains, capture interactions and transfer to robots? Or you think that language shouldn't play a role here? What is your view on this?
I think, and that's what we are working now, is to really connect more. I mean, it is, kind of almost separate line of work done by separate students. Yeah, but I think it's really now we are trying to connect these language-based or language visual models. And I think because we've seen a lot of visual data, they generalize well, but also trying to connect them with the more kind of geometric-based methods together. And I think this is, as I said, I think this is, the thing which may work, but of course the time will tell which will work best.
Do you see this as a the fundamentally right thing to do, or you see it as a practical thing to do because language is widespread and we have data? Yeah, I'm thinking animals can do this manipulating tasks if they don't have language. So I wonder what you think about it.
Yeah, so why I think and it may be that once we have even self-supervised models like Dino, I think is the one which kind of does not use language, but is self-supervised model. But in part, what we're using now is models like Clip, and the reason why we use them, and they've seen a lot of, hundreds of millions of images with language. And the reason we use them because they just work better. So they've seen so much data. I think they are one of the best working models there are. So, it's more practical driven.
Right.
And also it allows the language part of the models, and it's interesting. And somewhat surprising, they allow you to do some level of planning, like this this kind of step planning. Yeah. You can ask the model, how to give me the steps of the different tasks, and it can do it.
Yeah.
It doesn't have the connection to the geometry or the control. So kind of given this component, and maybe we can do without that. I'm not saying we can, we won't be able to, but I think it's more, it's practical, having this which works quite well, but doesn't have the connection to the real world. And methods like this, which do have the connection, the 6D pose, the geometry, I think it's sort of somewhat opportunistic to try to connect them. If it's really the final answer, I don't know. But
we have time for one more question, last question. Otherwise.
Yeah, I can ask a brief one.
And the extracting motion forces work was interesting. And how do you exactly compute the forces when you estimate the 3D pose and the pose of the human and the object? Is it automatic? And also seeing the follow-up work, do you think the computation of those forces can be introduced in a learning setting, or we should rely on reinforcement learning or physics simulation?
It's also interesting. It's a complex question. So so first of all, we do have some estimate of masses. So we kind of use an average human we get some estimate of the forces, but we sort of provide this estimates of the masses of the human and also some average mass of the hammer. Yeah. So so these are the rough estimate. And there is really like a model of dynamics which we estimate. And for this we use the tools for the trajectory optimization from robotics. And I think, we collaborated with a roboticist. I had high hopes initially, and it was interesting to get the machinery all working together. But in some ways, it was a little disappointing in the way the whole thing was a little brittle. Like it's, if you don't have, and we got it working in the end, but it wasn't easy. So I think, and the way, I view it is really kind of maybe the right way to do regularization because of the problem is that, instead of you just put a regularizer on, say, the velocity, Here, I mean, you have the whole machine of the dynamics, and you can put the regularization or say the accelerations or the limits of the acceleration of what the human could do, for example. But at the same time, I think in the end, I would say the future may be in the combination of these techniques, deep learning, which will allow you to generalize maybe a bit better into just the variety of stuff which you see in the real world there. So I don't think the pure optimization approach, and this is again personal opinion, it may not be the final answer.
Okay, thanks, and thanks for the nice talk. Bharat will introduce our next speaker. Thank you very much.
Hello everyone, it's my great pleasure to welcome our next distinguished speaker, Dr. Rhobin. Torsten is a senior researcher and heads the Spatial Intelligence Group at Czech Technical University. Torsten's work on visual localization, feature matching, scene representation, and rendering was truly inspiring. Thank you, Torsten, for joining us today. We look forward to hearing from you.
Thank you very much for the very nice introduction. Give me 1 second to try to set up things. And okay, so there we go. Yeah. Just need to turn off. Everything.
I can mute myself. You can just open the presentation.
I just need to. This thing always takes
It is
a bit of time to when you connect to something new.
Yeah. Is it stuck?
No, it's not
Okay.
stuck. It was stuck before. It restarted this morning, so it
Should be fine. Okay. Seems to move.
Oh. No? No? Come on.
PowerPoint.
No, it's
No.
this works like just. Are you muted or not muted?
Yeah, we can.
Because I'm not. I think I'm muted.
Correct.
Yeah, it's just that this thing always is a bit of fun.
It's a bit blacked out in this place.
Yeah, I'll try this. Unfortunately, it had to fix the whole thing.
The thing is that the computer doesn't show anything right now.
Oh, you mean the computer is that? No, it's just
Yeah.
wait.
Okay.
Give it.
Yeah. Sure. Otherwise,
Died this morning. Tends to die. Once you plug it in.
You want to use mine?
If it wouldn't come back to when I get access, it should work. I got it to work on another Zoom screen conversation this morning. Okay.
otherwise, I can also put the slides in my computer, email them. No way.
So it's the issue? Like it doesn't. No, the issue is that the PC is a bit bitchy.
easily start.
It's the same, like I bought my first Mac in 2008. Been upgrading ever since. I think with every upgrade, something goes bad.
Yeah, you should get a new one by the M1 chip.
Yeah.
It's just completely different.
Yes, I'm a bit afraid that it will rank a lot of software that I want to pay now.
It's okay.
Let's see. I'm sorry for the delay. Yeah, I have some water also if you want. Do you want to use any objects for demonstration? No. Thanks. Good.
Because I also think that it's kind of my thing. And the thing that we have to know everything perfectly, like the lowest thing, frictions for I think our mental model, right? Model is not heavy, but you see somebody carrying, so yeah, it's
Into the Zoom.
we don't have data.
So that's maybe.
Just.
This is actually nice. Yeah, maybe it's password.
Password. And like I want to create an animation, like very. It's sensitive to the way.
The Zoom works.
Like even by getting the pose, the noise in this degree was larger than these subtle differences. So then. Yeah, we think about like the simplified,
Closest, many things can be close.
Recording in progress.
I've muted myself here, so you can unmute yours. Okay, I'm very sorry for the delay. Yeah, thank you very much for the nice introduction. I'm happy to be here. I'm going to talk about visual localization. So let's start with like a short definition what the visual localization problem is. The localization problem is giving some representation of the scene.
For the Zoom.
Yeah. Yes, I can mute. Should I mute myself?
No, because I've muted here.
Yeah, they will not hear. Good. Is there still an echo? Okay, this is, I think, is the echo gone now? I think so. Okay. So one thing after another. Localization problem was given an image, some representation of the scene, we would like to compute the exact position and orientation from which this image was taken. And this has applications in augmented reality, where by registering an image onto a 3D model of the world, we're able to show virtual objects as if they were in the real scene. So this is some work that we did nearly 10 years ago at ECV. And if you have a Google phone nowadays, there's augmented reality walking instructions that you can get that will tell you where to go. Another interesting application and more related to this workshop is that you can actually also use it to figure out where humans are in the scene. Some work that we did with Gerard, where we have like one head-mounted camera for the human and then IMUs on the body. And by jointly reasoning about localization results from the camera and IMU information from the body, we're able to place these humans in large scenes without having to have external cameras. We just need a 3D model of the scene and the sensor setup. As you can see, like knowing where a human is if you're interested in modeling the interaction between a human and the environment or a robot in the environment, then you need to place that human in the scene, because that will give you very strong cues about the potentials for interactions that are around this person. And for this, you need localization. So let's talk a bit about localization. The most common one is what I would call structure-based localization. The idea is that we have some 3D model of the scene, and if for a given query image, we establish correspondences between pixels in that image and 3D points in the model, and these 2D, 3D matches can then be used for pose estimation using classical techniques. This all is based on building a 3D point cloud of the scene. This is typically built from images using structure for motion. So each 3D point was created by matching features between 2 or more images and triangulating them, which also means that each 3D point is essentially a position in space and the corresponding image descriptors. And if you have a new image, you can extract features. So given a new image, you do feature detection, feature extraction, and description, and then use these descriptors of the features extracted in 2D and the descriptors associated with 3D points to get 2D, 3D matches. And then you do pose estimation. I tend to call this the old school localization pipeline for the sense of that many of the components that you need to run it are quite old. So SIFT was originally published in 1999. And that's actually the oldest component in such a system. Feature matching you can do efficiently with KD trees, that's the 70s. Pose estimation, like the first principles of estimating the camera pose from 2D, 3D correspondences goes back to the 1700s. Ransack is 1981, it's older than me. So this is really, like, we could have run this like last century. Nowadays, you would use like a slightly different version of that pipeline. So you wouldn't directly match features to 3D points, but you would exploit, do some image retrieval steps. So the idea is that you don't not only store this 3D point cloud, but you also store the images or some information from the images that were used to reconstruct the point cloud. And then if you have a query image, you can first do an image retrieval step and say, okay, this is visually the most similar image to my query. Most likely, this is a place where I am, and I don't need to look at the rest of the point cloud. Then you do 2D matching between features in the query and features in this retrieved database image. And since you know which 2D features in the database image correspond to 3D points from the reconstruction process, you get 2D, 3D correspondences, which is all that you need for pose estimation. And again, like working versions of this pipeline that worked in real time back then were already presented in 2009. Nowadays, you're using learned components for all parts of the pipeline. You use learned featured image descriptors for retrieval, for example, NetFlood from Joseph's team. You use learned feature descriptors. You use learned matches, such as superglue, or some combination of learned feature extractors and matches, such as Lofter. And also for pose estimation, there are nowadays some variants that use learning in some part of the process. If you want to experiment with this thing, there are very good toolboxes out there, like two in particular, the HLOC pipeline from Paul-Edouard Sarlin and Capture from Naver. So this as a short introduction to the problem. What we now see emerging is like companies offering localization as some sort of service. So for example, like Google is essentially running this in their AR navigation system. Naver, Niantic is having some localization services that are becoming available. Microsoft through Azure Anchors, and they all work in like a similar fashion. You have a user that has some sort of edge device a mobile phone, like a virtual reality or mixed reality headset, they take images. Those are sent to some server that runs localization and has like scene representation stored, and that server sends back the camera pose and the client does something or something. A natural question, if you look at this workflow, is what happens to the privacy of the user? And there's prior work on this that looks at like two things. Like the obvious thing is that if I send an image of, say, my living room to some server, chances are that someone is going to analyze it and know what I have in my living room, which is maybe not information that I would like to disclose. So like sending images themselves is inherently a private risk. And there's some work on obfuscating the images, essentially extracting some level of information that still allows localization without allowing like a malicious attacker to recover detailed image content. The other potential privacy risk is user-generated 3D content stored on the server. So if you say you like to play AR games in your living room and you have a cleaning robot and you would like to reuse the same map built by the robot and for the AR game, you might upload this to a server, and obviously again come to the problem that someone might extract information from that map that you're not willing to disclose. And again, there's some work on trying to obfuscate these 3D maps in a way that still allows localization without like easily allowing someone to learn something from the scene. And in some work that we're going to present at CVPR this year, we asked that, like, assuming that you can obfuscate queries perfectly, assuming that you can obfuscate 3D maps perfectly, do you have like a perfectly privacy preserving system? And the interesting answer to this is actually no. There's actually quite a lot of information that gets disclosed just by like a 6-dimensional vector, which gives you position and orientation. And we are going to present like a very simple attack. It's more of a proof of concept, but it's based on the idea that we're trying to build localization systems that are as robust as possible to condition changes. So what do I mean? So what we're nowadays trying to do is we're trying to train local features that can robustly match between, say, day-night changes, or that are robust against like degradations in image quality, such as motion blur. And so what we're trying to do is we're trying to train features that can handle variations in local image appearance and local geometry appearance. And the downside to this is that you're not only matching things that are actually physically the same thing, but you're also matching things that are physically different, but very similar locally. So for example, you see feature matches between different parts of like I think a food court or something, where there are similar structures, similar locally, for example, the chair, but that are physically different. And that leads to a very simple attack where you can start recovering scene content just from camera poses alone. The idea is this. You assume that the attacker has some sort of image sequence of some object, some common object, such as a chair. The attacker builds like this local 3D model to get the relative camera poses by running structure for motion, and then queries a localization system with each of these images. The server will give you a pose for maybe not each image, for many of them, which are shown here. They are quite noisy because the object itself is not in the scene. But still, it's enough that you can align the poses that you get from the server and the poses that you get locally from structure for motion and actually place the object in the scene. It's not always super accurate, but it's accurate enough that you get an idea of what's in the scene. So here are some examples. Here you see the ground truth alignment of a couple of objects. They're shown here, the original thing that's actually in the room, and like one of the example images that we query with. And you see the two alignment results that we get with different types of local features and matches. And you see that it's not perfect, but you get a good gist that here is a door, here's some cabinet, here's a desk, here's a chair, and so on and so on. And I mean, this is treating every object independently of all other objects. You can probably do much better if you start reasoning about spatial relations of objects and where they should be in the scene. Here's another example where this is the actual scene. We highlighted the objects that are in the scene. And this is what we recovered with images of objects that are similar, but not fully identical. So again, you see that like this tiny bit of information that the server returns, like 6-dimensional vector, is sufficient to actually learn something about the scene. And I think that's interesting in the sense of that some companies are actually advertising their services. Oh, we're doing all these privacy preserving things. You're safe. And it turns out maybe they're not. Okay, so the main takeaways here is that if you want to ensure privacy of something stored on a server, you can't just return camera poses all the time. You need to be selective. You need to do some reasoning about, was this image really taken in the scene, or is it something different? And we haven't found a solution to this. This, I think, is a challenging problem itself. It's also unclear to us how much this actually means that the server has to be able to understand what's in the scene, which might create a privacy risk itself. So you need to have this type of verification. The other interesting thing, I think, is that there seems to be an inherent trade-off between building robust localization systems and localization systems that are privacy preserved. I don't think that you can have both. I don't think that you can have something that's like robust to all type of condition changes, because you'll run into this type of problems that I just presented. If you want to know more, feel free to ask either now or later, or come to our poster on Wednesday afternoon. So that was the first part that I wanted to talk about. The second part is kind of related to privacy, but more about scene representation. What I showed here is this classical way of representing the scene as a structure motion reconstruction, where each 3D point is essentially reconstructed from images. So you associate image information in the form of local image features with it. And this is like a representation that's built specifically for the localization task. You can't really use it for something else, such as occlusion handling or something. And it's built for a specific type of local features. So if you switch your type of local features, you need to recompute, which can be time consuming depending on the size of the map. You might be talking a few hours, you might be talking a few days, maybe a week, depending on how large it is. At the same time, it's clear that this is, and it's nice that it works, but it's a specific scene representation. In the example that we had before, where the human is walking through the scene, you would actually like to have a dense representation. One of the things that we're using here is actually a constraint that a human has to walk on the surface and can't just like float above it or penetrate the surface. For this, we need like a dense structure of the scene. So I think I would argue that to some degree, what you want is actually more of like a dense mesh-based representation of the scene, which you can not only ideally use for localization, but also tasks such as modeling human interactions in the scene, or enforcing certain constraints, such as the human can't walk through a wall if you're modeling human object interaction. And it turns out that you can use meshes quite easily into a localization pipeline. It's essentially the same pipeline as this retrieval-based pipeline that I showed before. You have a mesh of the scene, you have your query image, you do image retrieval to essentially figure out what are a set of potential viewpoints that are close to the viewpoint of the query image, meaning which parts of the scene are likely to be seen in the query. Then you, rather than storing the original images, you can just store the mesh. And if you want to do 2D matching, you just render like the mesh from the retrieved viewpoint online. That's like if you use classical rendering pipelines, we're talking about less than a millisecond for this. You do feature matching. And since if you render a mesh, you cannot just, you essentially get a depth map for free, at least in a classical rendering pipeline, which has a depth buffer. So you get 3D correspondences automatically, and you can do post estimation as before. And we explored this pipeline in ECV paper last year. And I think one of the interesting things that we found is that like modern local features don't just match real images against like reasonably realistic renderings of models, but you also get surprisingly many matches if you just render raw geometry in a shaded manner. And this, they like modern local features, learned features work quite well out of the box without ever being trained for this task. So an obvious question is, why is that actually an interesting observation? I think what makes it interesting is that it alleviates some of the problems that you have if you require a photorealistic representation of the scene. So traditionally, if you wanted to do localization, you have to go out, capture images yourself, which is time consuming. You need to run them through a 3D reconstruction pipeline, which is time consuming, but also not that easy for everyday users. It requires some getting used to run a structural motion pipeline or to run like a 3D meshing pipeline. And the models that you get are typically quite detailed, they're memory intensive. We're easily talking about a few gigabytes for relatively small scenes, but you get accurate 3D models. If you're lucky, you are interested in a scene where there are images on the internet. So for example, landmarks, which was like reconstructing landmarks was a popular thing about a decade ago. So there you can just download images from Flickr. You solve the data acquisition problem. Your images are easy to obtain, but you still need to run 3D reconstruction, and you need to have the knowledge for this. And you don't have control over whether you actually have enough images. And what this observation that modern features actually also match against non-photorealistic renderings, what this enables is that you can actually start downloading like ready-made 3D models that someone else did from the internet. So you don't need to do any data acquisition. You don't need to run any pipeline. You can just download a model, say, of Notre Dame, with the only problem being that you don't have any control over the quality of the model. So a second paper that we're going to present at CVPR this week is actually asking how well do these like modern features handle the type of imperfections that you see in 3D models that you get from the internet. And that can range from, so we look at like photorealistic models that were created from images to things modeled by hand with realistic textures, with less realistic textures, up to something that's just like a very few triangles or quads, or to things that are Minecraft-like worlds, things that where whoever created that model added some extra details that are not there in the world, and so on. So what we do there is we download these models, we render synthetic images from a predefined set of viewpoints, we get images and depth maps, and this is everything that we need to run this mesh-based localization pipeline that I showed you. And I think we have some interesting results. So here you see localization accuracy. What is shown is some sort of measure of alignment in terms of projection error as a function of the percentage of image diagonal. So you would like to be somewhere over there. See, for this photorealistic mesh, you can localize everything very, very accurately. If you go from this one to something that I would say this is something that I clearly recognize as Notre Dame, you're still doing well. Interestingly, like this thing, which is just raw geometry, which is this curve, gives you better results than this thing, because even if it has a realistic texture. So I think what we observed is that in general, like, geometric accuracy is not the limiting factor. Being able to establish correspondences is. And there's still like a lot of room for improvement until we can use something like this for localization. In general, we observe that if you start from a realistic model and then degrade it, so here you see the quality of renderings that you get if you start from the original model and then downsample the number of faces, you can handle actually quite a lot. You can handle downscaling the texture resolution quite a lot, but this combination of geometric accuracy and texture accuracy, that's what's going to kill you at some point. So the main takeaways here is that meshes are actually a viable alternative to classical image like scene representation built from images. And yeah, photorealism is nice, but you don't really need it. I think that's an important observation, because if you think of like building a model of the world that you can use for localization, where you can place objects that can then enable human object interaction, then I don't think that you really want to deal with building something that's photorealistic. And I don't think that you need to, as a human, I care more about shapes, I care more about outlines with some texture details, rather than having like a photorealistic memory of everything that I see. And this is what this research based on meshes, I think, opens the door to, that we can start building scene representations that don't need to be realistic, that are more easily to update, and so on and so on. But I think there's still a lot of interesting work to be done. I think we're just scratching the surface. Efficiency definitely still an open issue. And if you're interested in this, we're actually going to make the benchmark available, and there will be details on the poster on the Wednesday afternoon session. So that, thank you very much. And if there are any questions, feel free to ask.
Yeah. Yeah, thanks, Thorsten, for the nice talk. So I have a question about your last part. So I'm a bit surprised with the results. So you're saying that you don't need photorealism, but still all these like visual representation methods, my understanding is that they rely a lot on like local texture and local pictures, and they don't work very well when the object doesn't have this. So what are your thoughts? Like, how can we adapt these methods to work, for example, like with objects and that are more homogeneous without like these features that Notre Dame or like this building? How do we make them reason more about shape, right? And like global shape, not so local.
I think this is actually what's happening there if you're matching against this, that you get shape information from this. What we observe for this really untextured thing is that we can localize images that are taken far enough that actually see the outline of the thing, rather than like details. If you like if you're too close, this is not going to work. But I think it's really shapes and outlines that are the important things. And I think it's possible to train these type of local features to actually fire at these things. There was an interesting paper that showed that, was it ImageNet, like models pre-trained on ImageNet are biased towards texture rather than shape. And they showed that if they create versions of ImageNet with stylization, that it starts focusing on shapes rather than textures. And I think we've did some preliminary experiments. I think you can do the same for local features, that you start doing, like training them in this way. It's definitely one of the things that I'm interested in looking into, both from scene perspective as from an object perspective.
Yeah, thank you very much for the talk. I was wondering, when you were talking about the privacy issue with the phone basically sending all the data to the server, what about looking into more efficient localization methods that could run on your edge device already? I mean, you touched a little bit about efficiency being still an open problem involved, but what's your take on this?
Yes, I think that's one potential solution, like at least one potential way of looking at this. The problem is still you need to send this like the maps to this client, right? You need to keep them up to date, which like removes this like angle of attack of querying with some images that are not in the scene. But you still have to deal with privacy preserving representations that need to be stored somewhere in the cloud and then synchronized with the client that downloads them.
And why would I have to store these maps on the server? Couldn't I download them locally, or is that just too big?
I mean, it depends a bit on the application, right? If it's a single person using that scene, there's no need to store it on a server. Although you might want to send like data to at some point to server that reconstructs things if you look into larger scenes, right? once you start looking into multiple users, you need to have one way to keep, like a way to keep like a single version of the map that gets potentially updated and then shared. Maybe you can do this in a non-centralized way, but then again, you have to deal with access to the files and so on and so on. So you might still, for safety, want to have some privacy preserving representation of the theme, that even if someone accidentally or maliciously gets access, that they don't get any information from this. And then once someone gets access to it who should not have, then they could do the same thing as before and try to query with images and see what sticks based on the camera posts that they get back.
I see. Thank you very much.
Yep. Good.
There's some more questions. Then,
Thank you very much.
thanks again. So now we will have the talks by the challenge leaders.
Yes.
Okay, so we are moving on to the winners of the challenges of the workshop, and then we are going to have the posters in the West Exhibition Hall in the numbers like 170 to 184. Okay. For the challenge winners, we have 3 tracks. We have 4 winners. Two sorry. Yeah. We have 2 winners for human reconstruction, 1 winner for 6 degrees of freedom post estimation, and 1 for joint reconstruction. So we start with have 3 remote speakers and 1 with us. So Daniel. Yeah, okay, you wanna start, and then we can go with the remote people. Yeah. Huh? Hey, do you wanna? Okay, you wanna plug your laptop or I wanna. Okay, okay. So I can share the first videos, and then you can continue in the lab in the end. Okay, you can see it here. Yeah. Let's play first the videos from the winners. Okay, so this is the one of the 2 winning teams for the human reconstruction task. Okay. The 2 winning teams are one comes from NIP3T AR team, Hao Chen and Xia Ya, and the second team comes from NetEase Game AI Labs, Yingwei Fang, Qifang, and Yanjun Li. So I guess the authors might be in the audience. If you have any questions, we can take them in the end. So we're starting. Okay. It's okay. No, I think it's okay. Let me share the screen to Zoom. Sorry. Screen. Just yeah, perfect. Yeah.
Moving on to the second winner. Of human reconstruction in the task on human reconstruction and behave dataset. Okay.
Workshop. Our challenge track is 3D human reconstruction from single RGB image. The dataset has the following characteristics. Firstly, the data is derived from indoor video shootings, resulting in high quality and clear images. Secondly, the dataset images contain large objects such as tables, which may cause significant occlusion of the human body. Lastly, most of the human subjects are facing away from the camera, resulting in severe self-occlusion. Let me briefly introduce our method. First, we trained a neural network to predict the SMPL parameters and 2D key points of the human body in the image. Then, we optimized the SMPL parameters in camera extrinsics with known intrinsics based on the reprojection error. Finally, we performed ensemble on the results of several different key-point sets. In the following, we will introduce the details in the order of model prediction, optimization, and model ensemble. During the model prediction stage, our approach first predicts the 2D key points and estimates rough SMPL pose and shape parameters based on the top image. The predicted SMPL parameters are used to initialize the subsequent optimization process. While the 2D key points provide crucial supervision information to refine the pose and shape estimation. To achieve high-quality pose estimation, we employ the huge model of this pose as our backbone, which is pre-trained on large-scale datasets such as 3DPW and EFT. And fine-tuned on the behave dataset to adapt to the specific task of human pose and shape estimation. To further enhance the robustness and accuracy of key-point prediction, we utilize the quick test augmentation technique during the prediction phase. In the optimization stage, we made improvements to enhance the final results. Firstly, since the camera intrinsic parameters were provided, we utilized 2D key points in the original image space instead of a cropped image to supervise the reprojection error. This approach helps to reduce the global rotation error that may result from the camera perspective effect, as noted in clip. Secondly, we observed that the behave dataset has a limited number of subjects across different scenes. In order to ensure consistency of the human body shapes, we founded all video clips featuring a single subject and optimized them using same shape parameters. Besides, we add ground constraint to reduce ambiguity in single view pose estimation. Specifically, we train a convolutional neural network to predict foot contact from origin image on in-house datasets. And we obtain the initial ground by fitting a frame with ankle joints which are on ground. Then the SMPL and ground plane parameters are optimized jointly with a contact loss. Our experiment results show that this can reduce ankle joint error effectively. Finally, we employed a better optimization process, including selecting appropriate optimizers and parameter setting. We use different sets of key points as supervisory information, such as 25 points from open pose and 24 points from SMPL. Finally, we used multiple results through interpolation. Experiments have shown that this fusion approach can achieve better results than the best individual submodel. Thanks for watching.
And we are moving on to the winner of object pose estimation.
Thank you, everyone. I'm Nassim Chen, a postgraduate from the University of Science and Technology of China. We delighted to participate in this challenge and give a speech. Today will be discovering our method via canvas video net for the object Paris estimation. In recent years, with the advancement of deep neural networks, object Paris estimation has become a hot research topic, and existing research has demonstrated the good potential of safety Paris estimation using neural networks. In the head challenge, our task is to isolate the object Paris directly from a single object image. In our method, we model the problem as first detecting the unassessed normalized object coordinate space map from a single object image. In terms of object Paris using a random regression model, it is worth noting that we input the pre-plot object image and output their corresponding unassessed maps. Therefore, an additional explanation needs to be applied to the 2D search in the final 2D distributed correspondence. To address this challenge, we propose a template to the network. The pattern of our approach is as follows. We first encode the input object image into ingredients where we take features, such as 2D distributed correspondences and satisfaction attention. These features are then fed into a relevant hash model, which directly updates the object Paris. The 3D models mentioned here are used to render corresponding on-site maps and the surface attention maps on the training set, which serve as additional supervision signals to guide the training of the network. We successfully addressed the issue of object symmetry by classifying the point class of the object into different surface patches in surface attention maps. Furthermore, we employ a generated experimental network to address the challenge of occlusion, which will be detailed later. In addition to presented all-size map and surface attention map, we employ the forward data pre-processing method. Firstly, based on given maps, we use OpenCV to obtain the maximum bounding box of each object and deploy an average stretch to determine the position of the central point. To include more global context, we enlarge the scale of the bounding box by 1.5 to capture more interactions between the object and the background. Next, we utilize the enlarged bounding box to cross the image, including the unset map, mask, and angle mask. Secondly, we utilize Blender to render a portion of the synthetic dataset in order to enhance the realism and eliminate the bounding gap. We randomly select some real background image and then replace the object background with them. After obtaining a high quality synthetic dataset, we pre-train our network on it to enhance the precision of our results. This that furnishes a beneficial initialization for subsequent fine-tuning on real-world datasets. Despite the significant increase in dataset size achieved through the synthetic dataset, we further employ various data augmentation techniques to introduce additional components and foundation. We employ the coastal arts technique to simulate occluded or missing regions in the image. Additionally, we utilize Gaussian blur noise to fit the dynamic blurring of objects in the scene. Furthermore, we apply extensive color treatment to the image, altering the brightness, contrast, and the saturation. These techniques help the model adapt better to various occlusion scenarios and the noise present in the real world. Our network architecture is illustrated as follows. Given an input image and a mask, we crop out the region of interest and predict ingredient features to directly reflect the rotation and translation. We specifically choose a pre-trained coordinates as our backbone for this task. to facilitate the network spreading ability for approving regions. We refer a generated adversarial model to enable a full adversarial process between the functions ourselves and the predicted ourselves. During training, owners can be primarily divided into the geometry component and the game component. The game component is a straightforward generated adversarial loss, where the geometry component comprises a one loss with a penalty for owners, as well as logic for the intent implementation and translation. For each unique instance, we treat a model respectively. As shown in the figure, our model can accurately predict the 60 meters directly from Arch image and performance field on multiple object instances. In summary, we employ extended data pre-processing and augmentation techniques, significantly enhancing the diversity and scale of our datasets. Furthermore, we propose a neural network of GPD and employ adversarial loss for training an effective process prediction network. GPD has shown excellent performance in occlusion scenarios. Thanks for watching.
Okay, perfect. And we are closing with the winner of the joint. Of the joint task of humans and objects. No, just. No, I'm making it work. Yeah, I'm unmuted. So now you should be able to hear the voice again.
So what are we gonna do? Because we're already.
Yeah.
Like.
We are gonna, I mean, we have the doc, so I guess one can go to the poster session for a bit. Yeah. I mean, yes. Oh, okay. So you cannot see the script. Okay. Will you be able to make it without the script?
I think it was.
What are you going to? What do you want to do?
Home after, like, what are the limitations? When do we have to? Are you?
170, 184. We have
No, like, until which time?
until 12. I think I can until 1.
Until one.
We can have it after until lunch break. So it's a lunch break after, so we have it until 12:30 officially, but I think we can put it,
We can
push it, yeah.
And one question, like, the posters, like, they can be hanged for until 12,
Yes,
only until 12, that's strange.
yes. That's true. 12 is, I think it's true. Yes. But I can go there, yeah. But still,
I mean, we need to reschedule something, and either we have this talk at the end.
okay, yeah, maybe we can do it at the end, your talk.
Yeah.
Will you be
because
able to?
Otherwise, there's gonna be like zero time now for coffee break and.
Yeah,
At the end.
yes, at the end, after 12 will be okay. So I can take this offline and fix it, and you can have presenter notes and everything,
Okay.
and make it smoother, okay, great.
If it's day,
Yeah.
I think we should start, I mean, at the very least, not at 10:30. But at 10:40, I'm not sure. Yeah.
I will be here for Kristen, and yeah, we can start at 35 maybe.
Maybe we can ask them for her, which is probably fine, unless you.
Okay. Yes, that's what I'm worried about, because I saw she has a lot of talks today.
So you saw that?
Yes, but I'm not sure if it's like back-to-back talks. If you can ask her, that would be great.
If she's giving talk all the time. Okay, but let's have the coffee.
Yes,
break.
yes. Let's have the coffee break now and the poster session in the west building. Posters 170 to 184. Really nice works. Have 15 posters. And then we'll continue after 10:30.
But 10:35, right, we said?
Yes, 10:35, that will be the next talk.
Please be here, like, instant ground and we can, it's gonna be an awesome talk, the 10:35. Sorry, there's not so much time for posters, and they are in the other building.
It's my computer. At my computer, can you send me some links so in the email so I can print?
In case I'm not here, I send you the information.
Yeah, it's fine. And
Hello,
hey, Leah.
how's it going?
Good, how are you?
Good. It's a bit tight, the schedule.
We had technical problems.
Yeah. And I saw that.
After,
You always have to plan like, even if you talk like 5 minutes, it's like,
Yeah.
because there's always a question. But the pity that the posters are like so, like it's gonna be so short.
Later on, so you,
Oh,
I just.
I'm sorry.
It's gonna be very short for the poster section now.
So you moved them to, I just arrived those, I.
Yeah, it's not possible to, I mean, I would like to have the posters at the end, but
Let me check
my
if I can
understanding is that
do
it's
it in
not
my
possible.
computer.
Maybe people can start putting them out there.
Hey, hello, nice to meet you.
I'm Ethan. I joined your first 3D PW challenge.
Ah, yeah,
Like runner.
yeah, good, congratulations. Hello, I'm Gerard, nice to meet you.
Hello.
Hello.
Yeah, the problem is I cannot see the slides also. I cannot see the speaker notes. That's the problem.
Yeah,
In the one.
they were using, right?
For body.
per body.
So- No, from we didn't, it's not a CVPR, but we put it in context, so, like generate, reconstructing two people in context.
I remember that, yeah,
Yeah.
I remember that.
So
So
it's-
that's
the word
Yes,
yeah.
So that, so we put it in.
ends at 12:30.
You present our.
Yes.
Like, it's fine.
So
Yeah.
let me check now if you can do it. Is it soon?
Hello, hey, yeah. Great to have you here. So, we're a bit delayed. Is it okay for you to start at 10:25 so that we have time for people to come?
Oh, yeah.
Yeah, or you have a talk right now? It's fine. I think it would, yeah, so. We just finished, like, and the posters about the other side. So I would say like 10:35, the earliest. But I would suggest to wait until the room is. Okay,
What's the make this one?
Just this one, the green one.
No, it doesn't work. Have you tried this again? Have you done it? Have you practiced it?
Yeah, I did, but.
Yeah.
This kind of.
Because if you otherwise you will have to present without yes, in the West building. Yeah. 170.
No, I don't think so. Because they just said, like, people.
Yeah, she has sent it to everybody. Let me check again. Yeah. Or you can prepare in Zoom or you can connect your computer. How do you plug in your computer or? No,
Yes.
yes, it's on.
And did we make sure that they are hearing? Because I saw a comment in the chat. That
Yes.
we're not listening. Okay.
Because it was muted, yes, I muted their hearing. Okay, we're communicating offline. Maybe to Christian. Yes, she won't.
Yeah, I figured it out. Okay. Yeah, so.
So just have it ready for after. Okay. For the-
So I actually have to go to the poster session, so do I have to come 12? What is the exact time?
Yes, I can see you on 12. After 5 minutes after 10, 10 minutes after 10. So you can take your certificate, we can give you your certificate, you can do your talk and we'll tell you the details about the prizes.
Yeah, I'm sure I can take it at the end of that.
Yeah. Sorry for the confusion. Do you want We want to say that once in okay. So.
We have like, I think everyone is the poster session.
Okay, everybody's supposed to message,
I-
borrow the message, but
Okay,
we would
just
like
tell
to-
them to bring that back.
Okay, I told him to bring them back, yes. Okay, let me do a quick introduction.
Okay.
First, and then we can start. So, hello everyone. It's my great pleasure to introduce your next speaker, Kirsten Grauman. Professor Grauman leads the computer vision group at UT Austin and is also research director at FAIR. Her work spans across different fields, different research areas, such as visual multimodal perception, 3D vision, and embodied AI. Thanks for talking us today. Today's talk will be about human-object interactions in first-person videos.
right, hi everyone. Nice to see you here and thanks to the organizers for having me. So I'm going to talk about, as we see here, human object interactions and specifically in first person video. And I wonder if we're good on Zoom, if it's audible, any problems.
I didn't receive any messages.
Yes, okay, thank you so much. Okay,
Okay, good.
all right. So let me motivate then first person video itself and why we're so interested in it. So I'll contrast with what is our mainstay for many years, which is third person and often internet-based content, like the many popular and important influential data sets that I'm summarizing here, where we see the world as a spectator from the point of view of someone taking a photo or video. And while these are very realistic captures, they have a certain intelligence baked into them because they're curated about a certain moment in time in a certain frame of composition, and they're so-called disembodied, right? Because once we take these observations out of the context of what was happening, it's just a little glimmer of what was there. In contrast, when we think about first person or egocentric video, where you have a wearable camera on a person, like this head-mounted camera on a person going around the store, the properties are very interesting because now this is uncurated content. You see everything that comes through, and it's also long form video. So no more, 2-3 seconds at a time. We could easily have minutes, hopefully eventually hours in front of us. And really important, when we look at this kind of video, we're getting this front row seat to an agent's intentions, their goals, and their attention. And as we'll see in the examples today, of course, relevant for this workshop, even very nice hand-object interaction. So it's a domain shift at the least, and it has these very important properties for our research, I think, in addition to that. So why egocentric video? Well, in our work, we're motivated really on two fronts that might at the glance seem very different, but actually share a lot of things in common when we think about the perception problems. And that's on the left, robot learning. So being able to start to use human-centric observations to teach robots that can do human-like behaviors. And on the right, an augmented reality, where we want to be able to assist in the way that's just useful at that right moment for a user wearing AR glasses of the future, where we really have to understand their own context, what they're trying to do, and how we would give the right information or recommendation.
Sorry.
Yes.
Are you muted? Because if you're muted, I think that people in Zoom cannot hear you.
I got a yes from someone on Zoom.
Oh,
Can we, am I audible on Zoom? They can hear, this is good.
Awesome.
Yeah, thanks for checking. So the rest of this talk, I've got 3 examples I wanted to show you where we're trying to move towards fine-grained understanding of object interactions and in the wild video, especially first person. The first will be about a hierarchical feature learning technique with video and language, with first person video. And then I'll talk about aligning ego and exo content. So ego being first person, exo being third person. And I'll motivate that when we get there. And then finally, I want to give you an example of where we're looking at object interactions described in instructional videos. And so looking at the visual narrations that people give when they're giving you a how-to, and a challenge we have in trying to decide when they're talking about what they're doing or when are they not. Okay, so 3 components I want to highlight, and let's start with this hierarchical video representation learning. And for here, we're going to make use of a recent data set that was a multi-year effort from many institutions that we presented last year at CVPR called Ego 4D. And I'm showing you little tiny glimpses from what are long, 8 to 60-minute kind of captures from different camera wears, 931 of them around different parts of the world. And so this data set is unscripted daily life activity from the point of view of a wearable camera. And in total, comprises about 3,600 hours of content. And you can see that there's a lot of very rich hand-object interaction, because once you're wearing that camera, all your near-field activity becomes very prominent. And so you see people doing very interesting things with their hands to manipulate objects of all different kinds. Furthermore, you see a bit of the diversity that's present in this data in terms of geographic location, and indoor, outdoor, private, solitary home spaces, public spaces, social spaces with people, and interactions even with animals. So this is kind of a fly through of what this data set Ego 4D is like. Another important thing to emphasize about it is it's multimodal. So we do have the RGB certainly everywhere. We also have a lot of audio for some portion of the environments, 3D scans, a lot of IMU, some stereo capture, some multi-camera capture. There's one in here where you see multiple people having a meal, they're each wearing a camera. And finally, text narrations that I want to look at more closely now. Okay, so the text narrations are across all 3,000 plus hours of video. There's natural language description of every action the camera wearer does. And so in the white text, each of those are a narration statement. C is the camera wearer. So C dips the brush in the paint. C removes the fuel bottle. C opens the bottle left hand, etc. This exists across the entire data set. That means there's millions of sentences and they're time indexed with the video. This is a resource for us when we made the data set in order to index in and know what we had and build a taxonomy. But it continues to be a resource for multimodal learning, because now you have these parallel streams of free-form language and free-form unscripted video. Furthermore, what this text has is not just the play-by-play I've already shown you, but also video level summaries. So for every chunk of video that's at the 4 to 8 minute like chapter length, there is an overall description in language about what the whole thing's about. So, you know, these are very instantaneous, like I wiped the table, I put the hammer on the table, et cetera, et cetera. The video level summary will be something about the whole objective of what the person was doing in that whole longer clip. And it's the two of these together that are very interesting for us here, because we anticipate that what happens at that clip level description is very important for understanding the atomic actions. So here are 3 more narration examples, 3 sentences, 3 clips, and has been explored in some inspiring work that tries to learn embeddings, cross-modal embeddings that say, well, those language statements should be close to those respective video clips. So get those semantics of the language into the video representation. But what we can add here is the representation that captures the link between the overall description, that summary. Here's an example of one. So instead of, you know, fetch the water, put the onion, chip the chopstick, they were making salad dressing. That was the overall goal. And so our idea is to put these two things together in the way we learn a cross-modal embedding, because the low level will just capture the what happened. The higher level summary could capture the why. What is the intention of the person? What's all this action leading up to? So this was our insight. We can actually leverage both of these for cross-modal embedding learning. And you'll note that many, if not all of these kind of narration statements are about hand-object interactions. And we're going to leverage these 2 granularities. So we put forth in the conference, we have a paper in the main conference about this, higher VL, hierarchical video language embedding learning. And it's linking that what and the why. So at the child level, we'll do what others have done, which is to say, we want contrastive learning between the clips and the statements, get them close together in the cross-modal space. And then at the parent level, what we'll add to this is contrastive learning that will say for the sequence of text statements on the bottom, as well as the sequence of video clips just above it in blue, we want their aggregations in the learned feature space to also map close to the embedding for the summary text. So this is going to represent that higher level why, saying, okay, when you look at the instantaneous things, they should capture those semantics, but when you look at the aggregated sequence, then they should map up and map close to that summary. And this is the key to kind of represent both simultaneously, and we'll jointly train for both of these levels of constraints. So that's hierarchical VL. Now, if I show you a TSNE for our method on the left and for the existing method that looks at the contrastive learning only at the clip level, ego VLP, you can see that play out in the feature space. And it's just a 2D TSNE plot, but we can see how the summaries, which are those bigger circles, and their constituent child narrations, which are the smaller ones, are starting to group together according to their meaning, because we're requiring that these representations of the summary be consistent with those atomic sequence of actions. Whereas you won't get that, of course, if you're not looking at these higher level explanations in the text. So we took it to town across, different data sets and literature for Ego 4D, EPIC, Charade's Ego, and demonstrated some versatility of really how this pre-trained video language embedding can give you a good video encoding that's flexible across data sets and tasks. And for a lot more detail on this, please stop by the poster that Ashutosh will give on Thursday afternoon. Okay, so then let's look next at ego-exo alignment. And so here too, as this snapshot of a couple images suggests, we're still talking about a lot of rich hand-object interaction. But now we're up against this challenge that the visibility from one viewpoint to another is going to be quite different. And actually like a preview of the key insight here is that even though ego and exo is going to look so different, we think we can latch on to the hand-object interaction as the thing that allows us to understand them together. Okay. So we're motivated here by achieving fine-grained video understanding. So what's fine, what's coarse? Well, coarse would be what's often in many of our challenging video data sets of, from years past till now, things like you see, and this is UCF, kinetics, others, blowing candles versus swinging versus rope climbing, which have very important roles to play. But we also have to pay attention to, in other domains, to more fine-grained understanding of action. So think about a robot, or think about an augmented reality system where you want to be able to translate skill from some experts to the learner, where it really matters kind of these fine-grained details about the object manipulation. Like in pouring, is it the part where they're grasping the handle to where it's tilting, etc. This is a fine-grained action understanding. Okay, but getting there, this is hard. I mean, the differences are subtle. Visually, that's by definition, when we're fine-grained, we're looking for very subtle visual differences. And secondly, as I've alluded to, the viewpoint variation can be quite different. And in particular, we care about this exo to ego viewpoint change. In those two domains I motivated at the beginning, in robotics, think about the wish list to be able to take human video, so video of you or anyone else to showing how to do something, and then translate that to the robot's actions from its own point of view. And similarly for skill transfer between people, where we can imagine AR glasses of the future that would assist you with the right advice translated from what's observed in maybe a how-to video onto you, the user, in your egocentric perspective. Okay, so what I'm about to show you, you could think of any strong viewpoint change as being relevant, but I'm going to focus specifically on ego-exo as kind of dramatic instance of the viewpoint change that's motivated by these kind of applications. All right, so here's the goal. We would like to learn a fine-grained view invariant representation. It's going to be fine-grained, it's going to be frame-based. So we're going to learn a frame encoder that can be view invariant to these ego and exo perspectives and maintain the consistency of the action phase that's happening across time. And we'll do this by putting forth a feature learning objective that's built on temporal alignment. So here you can see at the top, sequence of frames from an ego perspective, at the bottom, also playing tennis, but somewhere else from an exo perspective. And our goal will be to learn an encoder for these frames that understands when these things relate based on the human object interactions and what they're doing, despite the viewpoint change. So if we do this well, then rather than the current state of things where any reasonable visual encoder is going to see mostly the difference in viewpoint because it's so strong, as these kind of little plots would show for two such videos. If we do this well, then we'll be able to align now and push these into a more view invariant space where furthermore the time step of these actions is close, right? And that's how there's some shading here from dark to light where time has moved on. And if it's the same action, then there'll be some alignment of these as we progress. So that is the goal. And we aren't the first to think about feature learning or view invariance and things, but the thing that's really important that we're trying to pursue here is to do this with unpaired data. So we'd like to have ego video over there, exo video over there, different people, different environments, but if they're both performing the same action, let's try to leverage them to learn this view invariant space. So that'd be unpaired data, unsynchronized, while still allowing for this very big view difference. Okay, so we're going to set up a feature learning approach. It's going to learn a frame encoder that has these properties. And important for this workshop, kind of one of the two technical ingredients we found quite important was to bring in an object-centric encoder. So we've already seen that when you talk about ego to exo, it's a non-trivial alignment or matching problem, right? Think of the person here sitting at the table and how much other stuff is there in the exo view. versus a different subset of stuff that's there in the ego view below it. But the thing that is reasonably consistent that we could hope to center this matching on is the hand objects manipulation. And so to leverage that, what we're putting together here, so you have the ego stream on the bottom, the exo on the top, and we're learning a frame encoder that's transformer based. And key to the first key ingredient is the loss is going to be about using dynamic time warping kind of loss to get alignment between these two. So we're going to search for representation that will put them into alignment as well as possible. But this first thing here is to add this object-centric encoder. And what that means is instead of pushing just the full global frame, we'll also have done some off-the-shelf hand-object interaction detection, and then have these regions of interest exposed explicitly to this representation learning. So for the hands, for the objects that are being used. And this actually had a really good impact on the kind of encodings that we can get out, because it's latching on to what's shared between the ego and exo perspective. And then the second key ingredient that we put here is a contrastive regularizer. So we had this self-supervised add-on to regularize this learning based on time warping that says, when we look to align a sequence here at the top from ego to exo, then if we were to reverse the frames of the ego, in my example here, then we know that the top two should have a lower alignment cost than the bottom two. Okay, and so this is a variant exploring, how we can self-supervise, just add supervision based on manipulating the sequences here, because we know that, if these are two videos from the same action, like they're both playing tennis or they're both pouring milk, then this should be true, typically, that when we reverse things, that the sequence alignment will be much more costly. Okay, so we put those two things together. We're in a single cross-modal embedding learning approach. And now let me show you what these learned frame representations can do for us for alignment and for fine-grained activity understanding. To do this, we looked at 4 combos of data sets. So there's the only new video that we're producing are some ego tennis videos over here. The others are taken from existing work and then coupled if they, in some cases where they weren't already, which is the bottom 2. So on the top, CMU, H2O, EPIC and HMDB on the left bottom, and then ours with some UPenn actions on the right. And in each case, it's a fine-grained action. So breaking eggs, pouring, and tennis. And for each, then we have these ego and exo views. And important to note is that we'll treat all of them as unpaired. So in CMU, you actually can pair very exactly because you have the same user from ego and exo, but we'll treat all the videos unpaired. And this means, especially in those bottom 2, which are rather in the wild from different settings, you have different people and environments between ego and exo. And part of the contribution to this work is we provide ground truth action phase labels for all of this. So action phase labels, these are things like for pouring, when is the liquid starting to leave the vessel, or when is the hand on the handle, and so on. So the individual stages, step by step of the action. And we do that not for training, but so that we can evaluate how well these representations are doing at crossing that ego-exo gap. So a huge table, not meant for human consumption in this room, but more to show you kind of a hint of how we evaluated. There's 4 data sets, 1, 2, 3, 4, ABCD. And then we looked at tasks for especially action phase classification, as I just mentioned, as well as variants like retrieving the frames. And as I'll show you in a second, can we synchronize the playback of an ego and exo capture from different places? And then the important comparisons we wanted to make is to know, how do we do compared to existing self-supervised learning with paired ego exo? So where you would want, where the requirement is that we observe things in synchronized form during training, to how we do compared to existing alignment-based video representation learning, which has not explored such drastic viewpoint changes among their training data. Okay, and so overall, what we saw from these trends is very consistent in terms of the accuracy we can do with this approach, the ego-exo alignment, and improving over the kind of baselines that I just mentioned across these 4 different data set pairs. The most visible way to see what happened is something like this. So here's an input pair, an input set of videos. So an ego on the left and exo on the right. And you notice they're not synchronized. And they're in fact, they're by different actors with different slightly different set of. Okay, so that was 2 input videos. And once we encode them in the space we've learned that I just described, and then do nearest neighbors to find alignment. So just think of every frame on the left video and then finding its nearest neighbor in the right video. Then we can play back as follows, our output, which is the synchronized ego and exo. You'll notice that to the level of when the egg is held above, when it's cracked, and when the other hand moves away with the shell, they are fairly well aligned. And so it's discovered, despite the viewpoint change, how to put the phases of this action in alignment. And indeed, kind of like my cartoon earlier, we're seeing that kind of shape to the learned feature space. Here, before ego and exo would just be, different parts of the encoding space, just with the regular visual features. But now you're seeing their alignment together in a viewpoint invariant way, as well as their alignment over time. Here's one more such example, the same format, input on the top, output on the bottom. Goes fast, let me do that again. Okay, so this is starting to get us, good headway towards being able to recognize these fine-grained differences, and furthermore, have the ability to link the action of someone else to ourselves in the AR kind of use case that I motivated earlier, right? To know exactly what part of the action that we're in. Okay, so then in this last bit, I wanted to share also some new work that is about understanding human-object interaction. It's some first person, but not strictly so. So this will be in general for video. And here we're going to look at specifically instructional video, which I find quite fascinating. And I think saw a talk earlier from Joseph in this space as well, where you see people showing very rich hand-object manipulation, procedural tasks, skilled tasks, and in many cases describing it as they go. And so kind of like in the earlier part of my talk, when I was talking about narrated ego 4D kind of video, here you also have narrations, but they're even more in the wild, right? Because it's just the transcribed speech from someone describing their action loosely or trying to teach you how to do whatever it is they're doing. And so examples of what they look like are here. Someone's talking about this sewing activity, 2 stitches on 2, and we'll slip stitch, and then stitch is going to, that must be an error. So you see they're noisy right from the speech recognition errors. And importantly, for what I want to show you now, they're not always talking about exactly what they're doing. And we know this, and this is an observation of, just how in the wild this kind of data is. But it brings forth a good challenge, we think, to study more closely, which is, can we detect when the person's narration describes what they are doing? Could we take a video stream and a narration stream from such an instructional video and decide which segments align in terms of the action actually being what is spoken? So here are examples where that is or isn't true. Like on the left, that's true. Here is what we would call a visual narration, because the person says, add 1/2 cup of diced carrot, and the video clip shows that. But other stuff's going to happen. Even though this is talking about pizza and the pizza's there, we would say this is not a visual narration because it's not the action of the person. It's just some useful information that has to do with which might be portrayed. So our pizza is now ready to be tasted. Well, that's not what the person's doing. This is also a non-visual. Here's a classic non-visual. It's just kind of, she's doing something, but she's giving more color commentary. Like, look at this, it's perfect. So delicious. Okay, so we want to know, can we take video, arbitrary activities, and detect when these moments happen that the 2 are together? If we could do this, I think it would be very nice for video summarization. I'll show you an example in just a few more slides. And potentially also for robots who are trying to imitate people. If you give a robot a how-to video and it starts trying to understand what all this part's about, it won't make good headway. But if it's only trying to pay attention to imitate the parts that are acted and described, then it should learn faster. All right, so let me tell you, so you kind of define this problem. A nickname for it in our model is what you say is what you show. That's what we're trying to find. And there's just 3 simple steps I can overview here for how we're going about this. The first one is to take some small amount of, not how to 100 million, but a smaller amount of key step label data and find clips where the key step name, the words itself, and the narration text are related. So if you had key step labels like this, like this segment of video has take out the wiper, and this just doesn't have any key step over here, Then you can look at the video clips and their narrations. And over here, you would say, well, that's not a visual narration because there's no key step present. And then over here, the language here and the language in the narration spoken by the how-toer are similar enough that we would say it's a positive for a visual narration. And over here, it's far, so we would say it's a negative. So we're kind of inferring labels from this weakly labeled data to come up with visual narration labels that we can then use to learn a cross-modal embedding. And we say, we want things to be close if they're visual narrations and vice versa. And then furthermore, where we can get even more power is go back to the massive collection in How to 100 Million and augment our training set for visual narration detection by pseudo-labeling this data with the original model. And this expands the scope. Many, thousands of more kind of tasks are present there. So what do these look like? So given that process of the kind of bootstrapping, finding out these visual narration sections, here's a bunch of positives. You can see these are all places where what's being described in the text below, spoken by the person, really aligns with what they're doing. Now add some salt, lift the car further up. Now we flip the pancake. Okay, these are positive visual narrations. And then here's some negatives. Whoops, back. Hello, my name is Mike. Oh man, it smells and looks so great. Did you peel the banana from the top or the bottom? So here too, you can see some, you might guess, well, I could say even from the language alone that sounds like not an action description. But then there'll be others where it's much more ambiguous. Like if you think about the words present in them, they're relevant to the task, but they may not be what the person's exactly doing. So we have to find out the difference between these two. And it does turn out when we look at our model doing this task, which is shown here in purple for its accuracy, compared to things like just looking at the words and a good word encoding or checking whether the named objects are present in the video with a good object detector, that we have this advantage by really treating it as a multimodal decision. Okay, and then finally, this lead, suggests what we can do for some video summarization. Where here I'm showing you frames with checks when we thought it was a visual narration and X's where we thought it was not, and they're kind of faded out. These are just showing you, represented frames from the whole how-to. And you can see that if you start to isolate the ones that are visual narrations, you've just kind of done a compression of the video into the steps that actually give the functional information. And what a neat thing, or possibility to let you look at a how-to and then get to the essence of what are the real steps. So for example, here, boiling the water, yes. Commentary about not liking to throw anything away, we don't need it, and so on. One more example in the same kind here is how to make Frito pie burritos. And these are all the clips that get selected as visual narrations that we detect. And you can see it kind of gets to the heart of what do you need to do, and here's what it looks like. As far as the ones we dropped, these are all the ones that were found not to be visual narrations by the model. And these are all things that are, more commentary, but also on the bottom, look, these have, added a little flour to make it thick. That's text only. That might suggest that a step's being described, but according to the video, it's not. And so we can start to tell the difference between some of these more subtle things. Okay, so I'm going to close the talk here. I've talked of examples, especially with first-person video, where we're able to start to leverage what we see in the fine-grained hand-object manipulations to do things like learn better video encoders, learn viewpoint and variant encodings, and form kind of understanding of the video as it relates to the core actions of the person versus anything else that might be described. The first authors, Ashutosh and Sherry, for the work that I highlight today, as well as other co-authors on the language-based work, and of course, all the members of the consortium for the Ego 4D project. Thanks so much for your attention, and we'd be happy to have any comments or questions.
Questions? You can use the mic here.
Yes. Hi, thank you for. I have a question about the self-supervised teacher learning, which you thought when you inverted the sequence for negative. And so the question is, what if the action is repetitive when you do the same thing with inverse? You can get both negative.
That is a problem. Yeah. So that should not survive with that kind of regularizer, and that kind of action is not present in the data that we have because they're kind of fine-grained enough and localized, they're not cyclical or periodic and so on. But it's a known issue in conceptually for generalizing where we want to take care of that, because you're right, then just a naive reversal would introduce problems. So something that we would want to kind of explore for future work. But thanks.
Thanks for the interesting talk. I was kind of curious your thoughts on when trying to get this shared understanding of egocentric existential views. Is there a role that like a more explicit kind of 3D representation would play there, or is it better just to kind of have the self-supervised latent features that kind of capture it?
Yeah. No, I think there certainly can be. So for example, if you were looking at these videos and solving for, camera parameters or camera pose changes, and then doing something more geometric about, even if you're putting in just a little learning, but to make these constraints, for example, maybe it doesn't have to be, what is ego exo? Exo can be any other view. So, I could imagine representing nearness of the viewpoint as part of the learning, etc. One thing to keep in mind is that because they are unpaired and unsynchronized, and in different environments, trying to bring these together geometrically is very hard, I think, and particularly from the ego view, at least our experience has been, relocalizing the camera with any amount of natural head motion remains pretty challenging. But all that said, yeah, I mean, I think you could look at how to blend more of the observed camera viewpoint changes into this learning, and it might help. Yeah.
Thanks for the nice talk. I would like to ask a bit more, like, if you can give us a bit more information about the representations that those models learn. Do they encode codes? Do they encode objects? Like, what do you think they learn really? Are they time scale invariant? Like, if I have an action and I slow it down, for example, will the features change, or can you give us a bit more?
Yeah, great. So for the ego exo one, it's a frame-based feature, so the time scale is not an issue there in the sense that it's instantaneous representation, whereas in the higher VL, it's a clip-based encoder, and so they're clip-based, like seconds long, I guess, per clip. So there, I think time scale would be more of a consideration because it's encoding to one descriptor for every single clip. Were you thinking of one of those two, or the visual narration as well?
Basically, like, I could give you an example. If I had a video of somebody pouring, I don't know, milk into a cup, will it have similar features with the video somebody pouring, for example, I don't know, water, like holding a completely different object, but doing the exact, like semantically doing the exact same thing?
Yeah.
Would it be similar in the feature space?
Yeah. And so there, do keep in mind it is frame-based, so then, it's learning kind of these instantaneous encodings of what it looks like at a stage of the activity. So this is good in terms of like invariance to speed of action, and that's what you saw in some of the alignment example. But as far as what is it learning? Well, we do know that when we do ablations, that if we throw out that object-centric region of interest, things are much weaker in terms of the downstream performance. So, I mean, with our helping hand, like to the model, that means that the ability to see the alignment or the agreement between the hand object regions is very important. So I think that is becoming part of what's learned in the feature. Like, do these look the same? Like, what I can expect then is like, is the relative pose of the hand with respect to the object with some variety in the object appearance? Yes, because of the data having that. Like, is it similar? And that would keep them together in the feature space.
Okay, thank you very much.
Thanks.
Hello, thanks for the nice talk. I have a follow-up question on this one. So if we, if the model learns some features about the hand pose, for example, and do you think this will help us at one point to improve hand pose estimation, like maybe with contrastive learning, if you know it's the same hand pose in some way, or is it too difficult to training data at this point?
Yeah, no, I think that's relevant for sure. Like if you took this as a tool to do alignment, period, like instead of thinking, oh, it's a feature space to do action phase recognition. Like if you take the temporal alignment out of it now, and then there's like a parameter space you care about, like hand pose, then you have the possibility to kind of augment the amount of data that you can serve to a model that's learning hand pose. So I think you could think of, I think that the temporal alignment can be seen as a tool towards data augmentation for training. Like say you have, moderate amounts of hand pose labeled video, and then you're aligning across viewpoints with this view invariant, then you could be increasing your ability to train for hand pose. Yeah, I mean, not something we've explored, but I can see that as like a relevant tool.
Thank you.
Sure.
With the next speaker because I'm a bit late. So yeah, we can have some discussion after the work we can do.
Thanks, Peter.
Okay, let me quickly introduce our next speaker while she prepares. Unfortunately, we couldn't have Cindy with us, but she's going to present us remotely. So I'm going to present you Cindy Tang, who is a tenure-track assistant professor in the Department of Computer Science at ETH Zurich. She leads the Computer Vision and Learning Group, PLG, at the Institute of Visual Computing. She has studied in Max Planck for Informatics, where she was supervised by Bernd Sille, and then she worked closely with Michael Black. And her research interests are in the area of human behavior and motion generations and statistical models of humans and their behaviors, either using machine learning or optimization techniques.
Hi. Can you hear me well?
Hello, see you? Yes.
Yes. You can hear me?
Yes. I hope everybody in Zoom can hear as well. It's like the sound is fine, okay?
Okay, good.
And you can see my screen. And yeah, it should be fine. Let's minimize noise. Okay, we're fine. Yeah.
So can I start? Or not?
Yeah, you can start. You can start.
Okay. Okay. Thank you. Thanks for the introduction. So I'm glad to be here to present some recent works from my group about reconstruction and synthesis human scene interactions. So this is an overview of today's talk. So I will cover two topics. The first one is reconstructing 3D humans in 3D scenes in egocentric view. And the second one is synthesizing 3D humans in 3D scenes. Okay, so like human pose and motion estimation is a widely studied problem. And the progress is fast. So we have more and more data and we have more accurate and efficient algorithms. So this is a very exciting area. And however, 3D human pose and motion estimation from an egocentric point of view, I think it's not well studied yet. So we don't have enough data for 3D ground truth data. And also we don't have like a lot of methods to do such tasks. However, I think like embodied sensors has a future. So it's important for embodied cameras to understand 3D human pose and motion from this very dynamic and embodied view. Right. So motivated by this observation, like we basically capture this data set, ego body data set. So ego body, human body shape and motion of interacting peoples from hand mounted devices. So the data set is already public available. So it has a very rich set of annotations. For example, we have a ground truth body annotation of both people from like a multi-view Kinects. We also have 3D scene information, and more importantly, like we have a egocentric camera, which is HoloLens. So this HoloLens is synchronized with multi-view Kinect, which means we have the 3D human pose and motion ground truth from this egocentric point of view. We also have gaze and hand tracking and head tracking. So I think this data set could be used for many different tasks. So for example, to understand 3D human pose and motion from egocentric point of view, as well as human motion modeling and human scene interaction modeling, because I think the motion quality is good. So it's not as good as AMAS, but it's already, I think, can be used for human scene interaction and human interaction modeling. Okay, so okay, now we have this data set. It's a large scale data set, relatively speaking, and like now the next thing we want to do is to really reconstruct 3D human pose motion, like later motion from this very dynamic embodied camera point of view, right? So these are just sampled images from the ego body data set, and you can see like it's actually very challenging to reconstruct 3D human pose and body from egocentric point of view, right? Because like we have this truncations, right? The camera is dynamic embodied, they have this big movement, quick movement, and also because of the social interaction, like the distance between people is small. So we also have like truncations and also human interact with the 3D environment. So there are lots of occlusions, right? So how do we solve that? So, I mean, here, the key idea is really to leverage the scene information, 3D scene information. So here's example given this input image, right? Because of the truncation, right? So the human could have this pose, but also on the right, this is also a valid pose, right? And the key idea here is to leverage 3D information. So the reason we are doing this is because first, 3D scanning techniques are developing very fast, right? So now you can use an iPhone to quickly scan the room, and also visual localization and mapping of, for example, AR glasses, embodied cameras, like it's also developing very fast. So we argue that a 3D scan of the scene can be obtained relatively easily, and which can actually provide very strong cue to infer the unobserved body part, right? For example, given this 3D scene information, we know like this person must have a sitting pose instead of standing pose, because if she had a standing pose, then her legs will be in the ground, right? Okay, so this is a motivation. And our goal is basically given in this work, given an egocentric image, RGB image, and a rough like a 3D environment, 3D geometry. Our goal is to generate like 3D human bodies in plausible interaction with the environment. And what we want is for the visible body part, it should align well with the image observation, and for the invisible part, right? For the occluded part, we should have a mechanism to do the diverse sampling, right? For example, given this image, this is a plausible poses, but this is, if you look at the leg, right? This is also plausible poses, and also this is a plausible poses. And why do we want to have this kind of a probabilistic modeling? There are two reasons. The first is, I think this is a right way to model that, because this really, we don't observe that, right? We don't want a deterministic approach to estimate that. And second reason is because later we want to do motion estimation, right? And to have a really good motion estimation, it's better to have this like a probabilistic pose estimation in each frame, and later we can get a better human motion estimation from this dynamic and embodied point of view. Okay. And the next question is, are there already some work to solve these tasks? So we found that most of the existing work for 3D human body recovery are deterministic, and ignore the diverse nature like of the missing body parts, right? And also like there are some probabilistic approach, but they typically do not consider the 3D information, so there is no seeing constraints, right? So motivated by this observation, we propose EGO HMR, so probabilistic human mesh recovery in 3D scenes from the egocentric views, right? So this side is the input, if you can see my mouse, so we have a RGB image and a rough 3D environment. And on the right side are the result. So basically our model can produce or can estimate accurate body pose bodies for the visible part, and we can also sample diverse plausible body pose for the invisible part. Okay, so what are the key ideas? So the key ideas here is to leverage diffusion models to effectively model the scene condition body pose in a probabilistic manner, right? So for people who know diffusion model, you know, like there are typically two ways to perform the conditional generation, right? Classifier free guidance and classifier based guidance. And in this work, we use both conditioning method. So we first propose a new scene condition diffusion models with a kind of like a joint visibility aware, like a graph convolution based denoiser to basically help us to really sample a diverse set of like unseen body poses, right? So this is the first part, leveraging the classifier free guidance. And also during the diffusion sampling, the diffusion sample itself is further guided by like a correlation score to further resolve the human scene interpenetrations. So the reason we use the diffusion model in this setting is because diffusion really provides us this flexible way and effective way to do the scene conditioning. Okay, so in the next, I will explain the details. So first, we have a scene conditioning model to encode the scene input scene point cloud into a scene feature and also predict the global body translation gamma. And then we have this egocentric image, and it's also encoded like into a feature vector using a CNN backbone. And we also run open pose on this image, right? So open pose have a kind of give us a rough understanding or estimation of which body part is visible, which body part is not visible, right? And all this information is basically, we use all this information as a conditional information to train this classifier free based diffusion model. So at each time step, conditioned on the scene feature and image feature and the joint visibility information, and the diffusion denoiser takes the noisy body pose parameters theta and predicts the clean pose parameter theta 0, right? So we do this multiple times, and in the end we can get like, this is kind of estimation we get given this input, right? Okay, so this is a diffusion model, condition diffusion model, and this denoiser we use a graph convolutional neural network, and here I am not going into the details about this part. Okay, so in the standard diffusion sampling process, so at each denoising step T, right? So the denoiser predicts the clean body pose, and which is noised back to the theta t minus 1 by sampling from a Gaussian distribution, right? That is a standard diffusion process without the correlation score guided sampling, right? And this can help us to somehow condition the body estimation on the environment, but it doesn't solve all the difficulties. For example, here, given this image and this 3D environment, we still have some human scene like interpenetrations, right? So the next, what we did is again to leverage this flexible conditioning mechanism for diffusion model. So we basically design like this to solve this issue. So we propose this human scene like a correlation score, right, to guide the sampling process. So now, like that, by calculating this gradient of the collision score with respect to the body pose. Now we can sample theta t minus 1 with additional correction term to reduce the collision in the next denoising step, right? So this is better actually than just like the post-processing in the end, right? We do some optimization here. We really try to introduce this additional correction term in the diffusion process to reduce the collision. So this sampling strategy basically help us to really produce plausible human scene like interactions. Okay, so here's just some examples result, right? So this is a input image and the scene environment, and this is also an input image, and this is a 3D environment. And you can see this as a result. So basically now for the visible part, our model can produce like a relatively accurate 3D body pose. And for the invisible part, now our model can basically sample diverse poses. At the same time, we can try to have like our model can produce kind of collision-free, like the model is the generated body is kind of conditioned on the scene geometry. Okay, so what's next, right? So now we have this model. I think what's next for us is basically now we want to estimate human motion from this egocentric point of view. Right now per frame, we have a nice model. And how do we do this motion estimation from this egocentric point of view? I think there are 3 things we can explore. So the first thing is to really leverage powerful motion priors, because in this egocentric setting, the person sometimes is in the camera view, but because this egocentric view is very dynamic, sometimes person moves out, right? And then we really need a strong prior to help us to filling in the missing observations. And also like to incorporate 3D semantics. So now we only have 3D geometry. And the next step is also to incorporate 3D semantics. And also hopefully to also incorporate physics information, right? Now we don't have any physics information in our model, but the next step, I think that would be something we want to explore too. Okay, so that's for the first part. And for the second part, what I want to talk about is synthesizing 3D humans in 3D environments, not reconstructing, but synthesize. So when I talk about synthesizing virtual humans, like people often ask me, why do you want to do that? Is it for computer games? Is it for character animation? Or is it for some applications for metaverse? So I think these are all very important applications, but for us, like in my group, we synthesize virtual humans in 3D environment is because we want to bring realistic virtual humans into real world simulators, right? So nowadays, if we want to train autonomous agent, for example, autonomous cars or robot, right, people often use simulations. And in these simulations, I think what is often lacking is realistic human behaviors, realistic and diverse human behaviors. And what we want to do is to really bring this realistic virtual human behaviors, into the simulation to further help the simulations to train like a better perception models, right? To help the autonomous agent to understand the world better. So that's the goal. So next, I want to put like our work in the context of computer vision literature and computer graphics literature. So traditionally, I think in computer vision literature, like people study motion is more like a motion prediction task. So given 1 or 2 seconds, right, we want to predict the next 1 or 2 seconds or slightly longer. So the goal here is really accuracy. So how accurate my prediction is, and also generalization. In terms of if I train my model on some actions, can it generalize to the actions that are unseen during the training? So the accuracy and generalization is the key, I think, in computer vision for motion prediction. And in computer graphics, it's like character animation. So it's an important topic in graphics. And I think the focus there is more on the motion realism and controllability. Right, because for example, for character animation, the motion realism is important because they want to have a good user experience. And controllability in the sense, for example, if the user controls the virtual characters, they want the virtual characters to really react to the input signal, right? So the focus in graphics for character animation, I think, is really on motion realism and controllability. So we have been working on like the synthesis in virtual humans for the past like almost 3 years, 4 years. And our goal, I think, is somehow like in between, right? So because our goal is really to learn a generative models that can synthesize diverse and natural human behaviors and bring these behaviors into simulations to help training the perception task. So I think the generalization is really important, right? So we want to have a generalizable generative model that can generate diverse human behaviors, human motions. And at the same time, realism is also important because the autonomous agent, they have to see realistic human motions, human behaviors in the simulation, then later they can be used, like the model they trained on such behaviors can be used in the real world. So I think both the generalization and the realism is important for our work. Okay, so I think I'm kind of a bit slow. So in the next, I will quickly go through this 3 work. So this line of work, the key idea is to combine a generative motion primitives models and reinforcement learning to train a diverse human, like a kind of walking or simple interaction model, right? So you can see here, our goal is to train a virtual human to go to the waypoint in the 3D environment. And this is the result sampled from our work. So basically what we can do now is like to have just one model, it generalized to different body shapes and produce a diverse set of behaviors. For example, someone walks fast and someone walks slow and kind of wandering in this 3D environment. So what are the key ideas for our for these 3 works? So the first key idea is marker-based body representation. So just give you an idea, what do I mean here? So basically we use a set of body markers to represent 3D body in motion, because these markers is basically just the locations in 3D environment, in 3D space. And then when we talk about human motion, it's just a translation in the Euclidean space, right? So it's easy to model, and it's also give a certain constraint on the body shape, as well as for example, the limb rotation. So the second key idea is generative motion primitives models. So what do I mean by generative motion primitives? So here are the generative motion primitives. So you can see like actually it's a model which you gave the model like the conditional information as the first 2 frames of the human motion, and this model predicts or generate next 8 frames. Plausible motions, diverse motions. So you can see like each row, actually the next 8 frames are different because it's different samples. And in total, this is 0.25 seconds. And the reason we are doing this is we want to generate perpetual motion, really long-term motion, like drive virtual humans moves perpetually in the 3D environment. But we tried to do that for 2 years. We didn't manage. We tried different GRUs, RNs, different architecture. I think it's a very challenging task, because what we see is when we train GRU like for a very short time, short-term motion prediction, it's very reliable. But when you go just beyond like 5 or 10 seconds, it doesn't work well, right? So in this work, what we did is this generative motion primitives models is basically, instead of ask the GRU to model long-term motion, so we asked this model to just model like really short term, 0.25 seconds. So hopefully the model is more reliable, doesn't really produce weird body pose, body shape, right? And for generating long-term motion, what we did basically is to run this generative motion primitives models in a recurrent way. So just a bit of details of this model. So this is basically a combination of a GRU and a variational autoencoder. So during the training, this is a conditional information, the first 2 frames, marker-based representation. And then this is the next 8 frame. And our model basically trying to reconstruct the next 8 frame. And we have a KL loss for the latent space, right? So the GRU basically try to predict next frame in a recurrent way. So one thing we find out is like we really need to go back to the valid body space after each prediction, after each time step. So in the CVPR 2021 work, what we did is basically to do optimization. So after each step, we optimize the simple body parameters so that we can fit the simple body parameters into the predicted markers. And then for the next time step, we basically take the markers from the simple body parameter instead of a predicted markers so that we kind of eliminate the errors, the accumulative errors of GRU, right? So we can do this. The problem of this optimization is it can be slow. So what we did in the recent two works is basically we use MLP to approximate this objective process, right? So this optimization process. So now this becomes the MLP and becomes much more efficient. So this is basically our generative motion primitives models. It's a variational autoencoder with GRU, right, to model very short motion. And now I put the whole generative motion primitives models into one block, this red block. So this is what you have seen the whole model in the previous slides. And so you can see this is like the first two frame, the conditional information. And then during the inference, we sample a latent variable from a Gaussian distribution. And then we can basically run this in a recurrent way. And now we can generate kind of like a perpetual motion, right? So really long-term motion, but these are all really random motion without any meaning, right? Okay, so the next question is, how do we really control this motion? These motions are all random. How do we really control this motion so that this motion can perform some actions to reach some goals, to perform some interactions? So how do we do that? So again, right, here, very simple, our goal is basically guided by the waypoint. So we want all the virtual humans to walk towards a waypoint in a very diverse way. So that is our goal. And without this control, without doing anything, right? So these are the motions generated by our motion primitives models. So all the human bodies ignore these waypoints. So inspired by this motion VAE work, now we model this motion control by the MDP formulation, Markov decision process formulation. So here the state of the MDP formulation is my body motion seat. So the two frames I already have, and my distance to the goal. So where is my goal, right? So this is my state. And the model itself is a generative motion primitives models, which generate natural human motion. And the action of the MDP formulation is a latent variable of the generative primitive model, right? And now what we have is we have to train a policy network. So that maps from the state to the action. So the way to understand is this is a policy network. This takes where am I and where is my goal? So what is my pose? Where am I and where is my goal? And produce me a latent variable, Z. And when I give this Z to my generative motion primitives models, my generative motion primitive models kind of drive my body towards my goal. So this is a key idea of the MDP formulation. And this is what I showed you before, right? So basically this model produces random motions without any goal, just random human motion, long-term motion. And now with certain goal, now you can see this Z is replaced by the sample from a policy network. Now this policy network maps from the state. So where am I? What is my pose? And where is my goal? To a latent variable. And now this latent variable goes to the generative motion primitives models, and the generative motion primitives models generates the next 8 frame to drive my body towards a goal. Okay, so this is what we did in the CVPR 2022 work. And in the recent, the recent development is we can really synthesize human motions in an environment. So now this state is basically represented not just by the goal location and my body poses, it also incorporates a local map, right, to make it scene aware. And also at the same time, the target is not just a waypoint in the 3D space, the target could be some body poses, like for example, sitting on the sofa, lying on the bed, some body poses that is generated by some other method. And this body poses, now this green thing is kind of like a guidance, right? The guidance in my policy network to produce a latent variable that drive my body to try to reach the target body poses, right? So now it's also interaction and scene aware. So next, I want to show you how this policy is gradually learned. It's an interesting video. So again, when we don't have the policy network, all the virtual humans just randomly move, ignore the waypoints, right? And then when we start to train the policy network, you can see the policy network just start to train, doesn't really produce valid latent variables action, so my motion is not really good. And when we continue training, it drives the virtual human towards the goal, but doesn't produce natural motion. And after like a long time of training, it's a bit very tricky to train this model. But after, if you train well, right, then all the virtual humans moves towards the goal, and as we want, they move towards the goal in a very diverse way, right? And hopefully this really reflects a real world human behaviors, like really reach the goal or go to a place in a very diverse way. Okay, so you can see this model also actually generalized to different body shapes. So for small and bigger person, and also general, I mean, here is an interesting behavior. You can see here is kind of trying to reach this goal in a very interesting way, and some humans walks very fast, some walks very slow, right? Okay. So, and this is like a new result. So a recent result. So this is one virtual human, but with different samples, and one target is sitting here, and one target is sitting here, one target is sitting here, and they walk in a different way. And you can see actually the last one is kind of wants to sit here. But actually, we didn't have a goal here, a target here, but this person basically kind of hesitating and then goes to sit here and then later sit together with everyone else, right? So this type of like a natural human scene interaction, human behavior is actually very hard to train and very hard to model. And that's what we can achieve at the moment. Okay, so I'm not sure whether I still have time to quickly go through this work. I mean, I think I might just skip this one.
Yeah, really quickly, like we can have one.
I think it's better to have time for questions.
Yeah,
because actually, like the next one is scheduled like 15 minutes ago. So I think
Okay, yeah, we can wrap up here.
Yeah, okay, so I will skip this like a diffusion-based motion synthesis. So yeah, so I will just go to the end then, because that's the last part of my talk.
We will have questions, so that would be interesting. It would be more interesting than I think a few questions, because the next topic is already late.
Okay. Yeah. So what's the next? So what I have talked about are the human motion and human scene interaction synthesis, right? So I think it's really important for this kind of work. It's really important to understand your goal, right? What is your goal? If your goal is to do, for example, motion prediction, accurate motion prediction, and what are the models, what are the data? If your goal is to do character animation or really bring think about applications in metaverse, and I think the realism and controllability is really the key. And for us, the goal is to bring virtual humans into real-world simulations to have the perception tasks. And I think in this case, the diversity is really important, right? To have the ability to generate diverse human motions and the generalization ability is also important. So I think there are many open questions. So there are really many unsolved problems in this area. So now we generate body motion and we also have hand motion generation. I didn't talk about here, but how about the whole body? So including body, including hand, even face, facial expressions, and also gaits. How do we build a kind of a holistic human behavior synthesis model to really model the whole body motion and like kind of social signal. I think that is very interesting task. And also go beyond just like reaching the sofa, reaching bed, but to do really long-term planning, right? To plan, for example, 10 minutes action, right? To really do this planning, and as well as social interactions, because humans, like we have social interactions with others, and how do we really also incorporate these social interactions into behavior synthesis is also very interesting. And another point I want to make is like, I think leveraging powerful generative models can be really like powerful, how to say, like, for example, our recent work, we use diffusion models, and it's really help us to synthesize very expressive and rich human motions. And the last point is I want to make is how do we really leverage the internet videos? Now everything starts from AMAS, right? But there are YouTube videos, right? Their behavior, like in the YouTube videos, in internet videos, how do we leverage those videos to learn human motion behavior models? I think it's an open research question. Okay, so that is the code, the data are all available on our our website. And thank you very much for your attention.
Professor Tan, suppose we found I have a question about antibody effect. Sorry, can we?
I don't really hear.
Don't hear.
Muted. Can you don't hear anything, see you?
I hear someone speaking, but I can't hear what it's about.
Okay. Can you try the question, and if she doesn't hear, we'll change and you can speak from here. Yeah, I guess. Can you ask the question?
Okay, my question is, I have been using the Agobody dataset for training a model to estimate really close animation global trajectory. I found that the camera motion in this dataset is quite unique because it's mounting on the human body. So is it possible? I found that your work has been using to synthetic human body motion, but is it possible to synthetic some camera motions, like in this unique situation, so we can model the camera motion, the pattern of camera motion, and further to explore the multiple interaction in this special egocentric situation. That's just my question.
I only understand there are some questions about ego body dataset. But what exactly the questions are, I cannot really fully understand.
So the question is that it's possible to generate camera motion.
To generate what? What motion?
Camera motion.
Camera motion. Yeah. Yes. I mean, if you can synthesize natural behavior models, you can synthesize natural human motions. You have the camera motion for free, right? You just put the camera on your virtual human's head.
But yeah, the camera motion is forming on it's implicit those human body motions, right? But it cannot pattern that those interaction between talking people, you know.
Between what?
The camera motion, when two people are talking to each other, they have to face each other and move the gaze towards.
So you are saying the camera motion has to have some interaction type of behavior? Is that what?
Yeah.
So it's I didn't present, so we can synthesize it. So we train our model to synthesize multi-human, like multi-agent behavior, and that is not like in the ego body, that type of interaction, right? Like a social interaction, but at least for people like walking together or working like moving in the same space, we can synthesize some natural multi-human behaviors. Yes, we can do that.
Yeah, thank you.
I think, Nikos, the microphone is from your laptop, right? Yeah. Can you hear me well?
Yes.
Okay. So great work, really interesting. I really liked the policy learning part. And I want to ask you, so if I want to walk to a target location, I will walk there, right? I will not fall on the floor and start rolling because it's weird. So there is some social aspects that kind of constrain my motion, but also some energy aspects, right? I don't want to spend too much energy to do that. But emotion prior doesn't know that. It could use any kind of motion to go to this place. So basically my question is, how do you constrain this motion when you're learning the policy to avoid doing weird things? Is there an extra reward there or what?
Yeah, so there are like a list of rewards. It's a rewards engineer, right? So one reward I think particularly helpful for avoiding weird body pose is, I think it's a Viposa reward, maybe I'm not right. So there is some like a body pose kind of regulated, like to try to encourage like valid body pose instead of weird body pose. And also we also have reward to encourage like good contact and no foot skating. So if it has foot skating and then it is a reward, like we don't have a high reward, right? So we have a list of reward to really try to encourage the model to have nice motion. And I think this reward is powerful. For example, now what we synthesize two people walking together, and then we can say the reward is like the people should look at the other one, and then you can see actually when you synthesize such human motion, it's kind of really interesting interaction happens.
Yeah, I guess, do you see any way of in the future avoiding this reward engineering somehow? Because on the one hand, you want this rich motion prior that can do a lot of things and produce a variety of motions, but on the other hand, you don't want weird things to happen to maximize reward. But do you see another way besides reward engineering?
So I have another role I didn't have time to discuss by time management. So we are trying two things in parallel. One is this generative motion primitives with RL, so with reward engineer like this line of work. That's one line of work. The other line of work what we trying is diffusion models, text to human motion. So what I find is the diffusion models is actually very powerful. So it can really very expressive and rich, so generate rich human motions. So I think if we replace our generative motion primitives, this GRU or VAE type of things, like this short motion generative primitives with diffusion models, I think there is a chance to really further improve the IL algorithms in the sense like the IL algorithms becomes easier to train, maybe less reward engineer, this type of things. But
interesting. Okay, thank you very much.
Thank you.
If there is no question, we can take it, but let's go to the next speaker because we are out of time. Thanks to you again for your nice talk.
Thank you.
And we hope to have you in person next time. Thanks, everybody. We are moving on to the final speaker of the workshop.
Just try it with Wi-Fi.
Why is not detecting? No. Yeah, it worked with the previous people. We can do the Zoom thing, space or Zoom. Oh no, it's fine. Cool. Okay, it's cool. Okay, you can just start presenting. And just go to your presentation.
Can you briefly ask the people in Zoom if they can hear?
Yeah.
Can you hear Zoom people?
Can you hear? Can you hear?
Out of the chat, they wrote something. Okay, the chat.
Yes, we can. Okay, yes, we can. Yes.
All right.
Okay, can you make it? Yeah, make the presentation full screen. Start presenting. I'm going to do a quick introduction. Edward Adolphson is the John and Dorothy Wilson Professor of Vision Science at MIT in the Department of Brain and Cognitive Sciences. He has published widely in the areas of human vision and computer graphics, and his current research focuses on artificial touch sensing for robotics. That is the presentation is going today. It's going to be about new technology that he's recently researching on, which converts touch to images and enables robots to have tactile sensitivity exceeding human skin. So, yep, let's.
All right, thank you. I'm going to try to be quick because it's late, it's lunchtime, and because my topic is so different from everyone else here. Anyway, so I haven't been to CVPR for 10 years. I used to be a regular here because I used to be a vision guy, and now I study tactile sensing. The reason is because when I had kids, I got fascinated with their sense of touch, the way they use their fingers. And here, for example, is Rhobin. She's 1 year old here, and she's never seen this kind of pasta before, but she very quickly figures out how to master it, how to use her fingers, including her sense of vision, her sense of touch, and she quickly figures out what to do with this pasta. I was just fascinated by this capability and wanted to know how to study it. And so I thought, okay, let's build some robot fingers with a sense of touch. And since I'm a vision guy, natural way to do that is with vision. So you, in this case, you take a chunk of clear rubber, put some special paint on it, press this Oreo on it, look from underneath, and then use computer vision techniques. And in this case, we use photometric stereo to extract the 3D shape. And so this can be used for touch sensing. It gives you, its natural language is geometry rather than force. People often think of force as the most important thing in touch, but really, I think geometry is more important. And anyway, so we can extract three-dimensional information in real time this way. And so at this point, my lab just works on robot fingers, using them for touch sensing and manipulation. Here's a gel-side finger holding a ruffled potato chips, and you can see that it's pulling out all the information, high resolution about the ruffles on the potato chip. As a vision person, it took me a while to think about, figure out how to think about touch and robotics, because my first thought was, well, touch is just sort of like vision, except your finger is like a retina, but it's really crude, it's low resolution, and there's a strange way of acquiring data, which is to come in physical contact with things. So that was my first thought. And then as I thought more about it, I realized, oh, really, these things are totally different. On the left, you see, well, a vision person looking at tomato is going to see the way it's shaded, the way the light's coming onto it, the way it's reflecting off of it, the way the different wavelengths are reflected, the occlusion. And the roboticist is thinking about using fingers to grasp the tomato. Tomato is thinking about, well, there's the force of gravity, there's the smoothness of the skin, there's the softness of the flesh as you press into it, deformation and so on. So that the topics just seem completely different. But then on third thought, they're actually almost the same, because vision really isn't about light. It's really about inferring objects and materials in the 3D world using visual data. David Marr's phrase for this was that sight is knowing what is where by looking. And tactile sensing really is not about force. It's also about inferring the objects and materials in the 3D world using touch. And so we could say it is knowing what is where by touching. So in that sense, they're very similar. And they come together because they're both concerned about the 3D geometry of the world. What is where? So when you see this tomato, you have all the visual and the mechanical properties of the tomato situated in 3D space. And in manipulation, actually, the geometry is usually what you're most interested in. If you hold a pen, you're capturing through your fingers its shape, its pose, the compliance, that is the hardness, the texture. Motion of an object that's a geometric thing. Slip is a particular kind of motion, again, a geometric thing. Force, finally, yes, there is force, but force can be inferred from these geometric distortions. And for example, here's the hardness of a tomato can be judged by geometric means. On the left is a soft tomato being pressed against a gel site sensor, and it squishes as it's pressed. On the right is a hard tomato that is an unripe tomato, and it keeps its shape as it is pressed. And it's this changing shape under pressure that allows you to tell the hardness or softness. And well, we did some machine learning with actual soft and hard objects to figure out how to estimate the hardness of different objects. Here's Wenjin Ron first ordering these avocados with her hands by feeling which one's harder, and then testing it with a gel site sensor using that machine learning system. And we don't have ground truth on whether these exact hardnesses are correct, but the ordering we get this system is the same as the ordering you get when a human places them in order. So there's an important property of objects in the world that you can extract with touch. And more generally, you like to be able to know everything mechanical and geometrical about the objects that you're contacting. So on the left is a wedge-shaped gel site sensor. The colored image you see in the middle, those are 3 colors of light that allow us to tell the surface normals and extract the 3D on the right. And of course, we've also got these markers, and the motions of the markers tell us about how the skin is moving sideways. So we've got X, Y, and Z information about displacement. And if you have an object, you know what the object's shape is, and you know its starting pose, then just by looking at this little bit of touch information on the right, you can track its pose. You can figure out how it is changing. So you can get a huge amount of information out of touch. And you can use it to infer important things like slip. Here's a sensor trying to pick up an object, but the object is slipping. And so you see the motion of the object impression on the right and the motion of the markers, which is different, which tells you you've got slip. We've used tactile sensing as feedback signal for various tasks. Here we're doing some cable manipulation. And as you slide this cable between the fingers can tell where it is, how it's sliding, what the forces are, and so on. And then you can use that signal for reactive control. You can keep this cable in the middle of the fingers because the robot can tell how it's moving. And then we can also, through other stuff that I don't have time to talk about, we can also find our way to the end of this cable and plug it in, even though it's a very noisy signal. All right, how about domestic tasks like folding laundry? That's a very tactile task. You really need to use your fingers to keep track of where you are on the towel. And here we're training a towel, these fingers learn what a towel feels like. Different parts of the towel feel different. Corner where things are folded over is different. The edge with a single fold is different. You've got two layers together on a fold, that's different. So here the fingers here are learning to feel its way around a towel to tell where it is, what part of the towel it's on. And then here we can slide down the towel, keeping track of exactly where the edge is until we get to the very corner. And then the corner feels different, and the robot knows that when it has felt its way down to the corner, it knows that's the right time for it to do the folding. So just to summarize, vision, of course, can capture the optical aspects of what is where in the world. Touch can capture these mechanical aspects of what is where, and these kinds of information can be brought together because they're in a common 3D frame in the world. You can get all kinds of good stuff out of tactile data, including shape, pose, texture, hardness, slipperiness, and so on. And you can also use touch as a feedback signal in a manipulation task. So thanks a lot.
Thanks for the talk. So you present these sensors, which are like, I don't know, maybe like 2 centimeters by 2 centimeters. If you wanted to instrument, the human hand has these sensors across, basically the entire skin. So how do you think you would scale up to more than just, these square finger pads?
So that is a key problem for this class of sensors, these camera-based sensors, which they tend to be bulky, and it takes a lot of effort and a lot of cleverness to try to make them more streamlined. We are doing that. We've done that in various ways. You can have you have a lot of small cameras embedded inside of a hand. Probably for large areas, like maybe the palm and the arm and so on, you may want to use other touch technologies. This technology is particularly useful when you want high resolution and you don't need it to be really compact. So, thank you.
Yeah, thanks for this interesting talk and this different perspective. So let's say like you want to synthesize, for example, like realistic human motion in like some environment. What are your thoughts on like how would you like include like this touch feedback in this virtual agents? Like, what do you think it makes sense? Like to sort of try to simulate like this like touch feedback, right? So that potentially the animations look more realistic.
Okay, so touch can be used, I think, various ways. First of all, of course, you can instrument objects to have touch sensing. So when somebody picks up the object, the object tells you how it's being touched, how the fingers are contacting it. these sensors are a little clumsy, but you can make a glove with sensors like this. So somebody using the glove can grasp something and you can tell what the forces are when it's grasping. In robotics, that's, it's very useful because robotics, of course, uses vision all the time, but when you're grasping things, you can't see what's going on because the fingers are hiding. So having a camera inside the finger looking out and sensing the distortion and forces gives you information about exactly what's happening with the robot.
So these are like, are they very expensive, these sensors, or basically?
So right now, almost all the time you have to make your own.
Yeah.
There is, which is of course fine if that's what you want to do with your life. That's what I want to do with my life, but you probably don't.
Yeah.
There is a company that I helped found that is making a simple box-like sensor that can be used.
Yeah, I'm asking because like for modeling things like human object interaction, I think it would be very useful to have this additional data, not just like with 3D reconstruction, but also like the forces and material properties of objects. Because all these things are important. If you have to transfer like human motion to a robot, you have to also know about this. That's all.
Yeah, I think it's at this point, it really is a research project, and unless you happen to want this small device that the company, which is called GelSight, does make.
Good question. The motivation you are saying that I found is not the forces, but in reality, according to the force that you are having, the footprint that you can have with your sensor could be different. And when you were showing also the slippery, probably you are using that modulation to understand whether the grasp is enough firm to handle the object. Is this correct? Are you leveraging on that?
Yeah, so I don't want to say forces of no importance. What I want to say is many people, when they think about touch, they think forces because all of it's important. And I think geometry is at least as important as forces. And you can also extract force from watching the geometry if you know physical characteristics of your device. But it is interesting when you I'll give an example here. All right, this has water in it, so I won't do too much with it. But if I hold this, I squeeze it strong enough so it doesn't slip. In fact, in this case, I can't do that. I have to have my finger under. But I can tell if it's slipping because I can feel whether it's slipping. It's not that I have in my head some idea, oh, I need to exert a certain amount of force to prevent it from slipping. In real time, I experimentally find out how much force I need. And so I change the force until it stops slipping. But I don't actually know what the force is. I just know, oh, that's the right amount of force to use. And of course, if I squeeze it too much, because it's paper cup, it'll start to distort, it'll start getting squished. And again, I don't know how much force, I can't tell you how many newtons of force I should exert before it squeezes. But I can tell the geometry and say, oh, it's starting to get squeezed. I should use less force. So I think geometry and force are both important, but you really need both.
If there are no more questions, we can thank the speaker and continue to the super question. Okay. Thank you very much. Okay. So now we're gonna have the winner from the joint reconstruction of objects and humans. Presented by before, and then we'll continue with the accepted papers, and then wrapping up. Thank you.
You think I will figure this out? Hmm? Yeah, do it yourself. Then, okay, so we're moving on with Daniel and yeah, 5 minutes and then questions. Yeah. Mhm. The option, because it seems like it's like oh yeah. Can you open it? Okay. Okay. Oh, yeah. Um, I don't know. We cannot see one. Okay, we can now. Perfect. Okay, let's go. Yes, you can start. Hmm? Hmm?
Yeah. Hi, I actually wrote good morning in the script, but it's good afternoon right now. So good afternoon. We are the winner of Joint Reconstruction track for the first Rhobin challenge under the supervision of Professor Young Lee in Seoul National University. The team includes Hyungjin Nam, Daniel Sang-Jung, Hyun Kim, and our supervisor, Professor Young Lee. I'm Daniel Jung, and I'll be presenting this talk. Our method, which is named CORE, stands for Key Point-Based 3D Human and Object Mesh Reconstruction from a single RGB image. Yeah, we will first briefly talk about the task of joint reconstruction of human and object. Given an input image, as can be seen from the left figure, our task is to jointly reconstruct 3D human and object mesh from the given single image. Here, it is essential to learn the interaction between human and object without any sacrifice in the overall reconstruction performance. In order to solve the 3D human and object reconstruction task, there are two straightforward approaches. First, we can directly estimate mesh geometry under the representation of distance field or mesh coordinates. However, this approach may be prone to falling into local minima with complex 3D geometry. Another simple approach could be to first estimate pose of human and object such as human joint angle or object 60 rotation, and then to extract mesh from the predicted pose. However, despite its simplicity, it often fails to preserve local context within the input image with the use of 1D image feature. In this work, we propose a novel key point-based method that allows the use of simple target geometry, which is key point representation, while preserving local context with our heat map estimation. Now we will go through the overall architecture of our method. We first start with the feature extraction. Given a concatenated input of image, human silhouette, and object silhouette, we use HRNet pre-trained on ImageNet for our feature extraction. Then the extracted feature goes through HKNet, abbreviated for Human Key Point Network, that directly estimates 3D key points of human from the designated human heat map. This effectively preserves local context within the input image. Similar with HKNet, our OKNet, abbreviated for Object Key Point Network, directly estimates 3D key points of object from the designated object heat map. This also effectively preserves local context within the input image. In the end, we have the key point networks, HKNet and OKNet, that estimates 3D key points of human and object respectively from the concatenated input of image, human silhouette, and object silhouette. Lastly, we have the mesh conversion stage that converts the predicted 3D key points from HKNet and OKNet, along with simple shape parameter and twist parameter for the following hybrid module. These estimates will be used to extract 3D mesh via hybrid module for human mesh and key point fitting algorithm for object mesh reconstruction. These are the qualitative results of our method core on representative samples from the Behave dataset. As aforementioned, we first predict the 3D key points from the input image. Then we extract the 3D human and object mesh from the predicted 3D key points. We can see from the results that our method has robust performance in general. These are the qualitative results of our method core on challenging scenarios. We can also see from the initially predicted 3D key points from the input image. Then we again extract the 3D human and object mesh from the predicted 3D key points. We can see from the results that our method shows robust performance under challenging scenarios, which are highly uploaded samples. To summarize, our method 4 shows robust performance on Behave dataset, whether it is just the simplest interaction between human and objects, or highly uploaded scenarios, such as shown in the right column. This is the quantitative comparison of our method compared to the previous state of methods. As can be seen from table 1, our method outperforms previous methods such as BOSA from ECCV 2020 and CHOR from ECCV 2022 by a huge margin. Here we reduced the chamfer distance, which is the main metric for this task, by 19.17% and 18.20% respectively. This is the efficiency comparison of our method compared to the previous state-of-the-art methods. Our core significantly reduces running time, unlike previous method, which involves more than 2,000 NFEs, the number of function evaluations, due to its nature of optimization-based strategy. Our core only requires a single network forwarding and results in remarkable reduction in running time by a factor of thousands. Yes, and this is not a typo. To summarize our achievements, we achieved the first place in the joint reconstruction track in Rhobin challenge with our novel key point-based framework. Notably, our methods have exceedingly short running time compared to the previous state-of-the-art method. This was our method in the Rhobin Challenge leaderboard. And thank you for listening to our presentation. And for more details, please contact us at cv.smu.ac.kr. Thank you very much. Is there any questions?
Okay, if there are no further questions.
So the twist is actually one of the parameters for hybrid, which was presented at CVPR 2021. So twist is basically the decomposition of inverse kinematics process of human joints. So we have to predict the twist parameter in order for us to utilize the 3D key points to reconstruct the final 3D human mesh. Thanks.
Okay, let's thank again the winner. And continue to the accepted papers presentations is Alexander here. Yeah.
My presentation on a flash drive. I think that might be easier than setting up my laptop and all that.
Yes, yes, you can use mine and you can just plug it in here.
Get wrong the first try.
It's always wrong with this time for some reason. And then you can use. Yes. Should show up here. Yep. Okay.
Great.
Do you have presenter notes? Do you want to?
I should be fine without the notes.
Full screen here.
Just like this.
Yep.
Maybe.
Oh. Okay, how weird.
think I got it.
Okay. Yeah, did it work? Okay, up and down.
Up and down.
Yeah.
Got it. Hi, everybody. My name is Alex Avery. I'm here to present Deep RM, Deep Recurrent Matching for 6D pose refinement. This work focuses on 6D pose refinement using a single RGB image as input. In addition to the RGB images, it does require textured CAD models of target objects. Our main contributions are a novel recurrent architecture that directly regresses 6D pose updates, the first scalable architecture designed for 6D pose refinement, competitive results on a couple challenging data sets, and a variety of ablation studies, a couple of which I will present and discuss. For background, I need to introduce the render and compare process. This was introduced by Lee et al. In their work Deep Iterative Matching in 2018. Since then, virtually all RGB-based refinement techniques leverage this approach. The diagram on the slide illustrates this process with information and time flowing from the left to the right. As inputs, we have an image of an observed scene containing target objects, along with a set of initial course poses for each of those objects. The course poses are used to render an image containing the objects that is consistent with the optical characteristics of the observed image. The rendered and observed images are then passed through a neural network to predict a rigid transform that reduces the error between the rendered and the observed images. Excuse me. This is shown on the slide here as the delta pose update coming out of the network. Because we're just predicting a delta update, we can repeat this process iteratively to refine the result. This method compensates for lack of external information such as depth by leveraging pre-existing geometric and visual properties of target objects via their textured CAD models. Our overall process follows deep IM, except we make quite a few modifications to improve the process. The main one, our main contribution is highlighted on the slide in red. This is the introduction of recurrent features into the framework. Our theory is that added gated recurrent mechanisms such as GRUs or LSTMs to iterative processes should either maintain or improve their current levels of performance. Consider the scenario where all gated connections are disabled. We simply have the original network configuration, which has already been proven to work well. We can then slowly open those gates and focus on learning only the information that's necessary to improve performance from one iteration to the next. And that's exactly what we do during training. This work here focuses specifically on 6D pose refinement. However, we believe that this concept should generalize to any iterative process. Getting into the details of our architecture, we take the rendered and observed images and concatenate them to form a six-channel tensor, pass this through our backbone to extract feature maps. The final feature map is flattened and passed through 3 shared fully connected LSTM layers before the final rotation and translation heads. This is shown across the top of the diagram. Then we also use those multi-scale feature maps coming out of the backbone to in an auxiliary optical flow head during training. This is shown on the bottom branch there of the diagram. The optical flow head is removed during inference, so its only purpose is to reinforce the training process. And as our backbone, we use the efficient net architecture. That's shown on the top left is the backbone there. Efficient net provides a way to scale resolution, width, and depth of a baseline network using a single scaling factor phi. The channel dimensions shown on the slide in red, highlighted in red, represent 2 of the efficient net configurations, efficient net B0 and B3, which correspond to the phi equals 0 and phi equals 3 efficient net configurations. And additionally, we extend the framework to work with our pose regression and optical flow heads. We train and evaluate on 2 data sets, occlusion line mod, shown on the left, YCB video, shown on the middle and on the right. In addition to the base training sets, we extend both heavily with synthetic data. For this task, synthetic data is absolutely critical. I'm going to skip results because you can find those on our poster and in the paper. I'm going to show a video next, so I'll skip the refinement sequences. Last slide here. This covers a few of the ablation studies that we performed. The goal is to demonstrate the efficiency and the scalability of our method. So we show the backbone architecture with the different efficient net versions, B0, B2, B3. We show the impact of using LSTMs or GRUs over standard multi-layer perceptrons, that is without recurrency. We show the number of trainable parameters for each of those configurations, along with the number of refinement iterations and accuracy and frames per second. The refinement iterations are the 2, 4, 6, and 8 shown on the top right there. Best results are achieved with the efficient net B3 backbone using LSTMs. And generally speaking, we believe the best balance of performance and accuracy is the efficient net B3 version using LSTMs, but only for refinement iterations. This is what's highlighted in red. We achieve 86.2% on the YCB video data set with this configuration at 18 frames per second. So 86.2 is still better than all other state-of-the-art approaches, except for one, gotta say that. And the 18 frames per second means it's useful for real-time applications. Finally, the table on the bottom shows the impact of varying the number of iterations, refinement iterations during training and testing. Best results are achieved when training with 6 iterations and testing with 12. We weren't able to train out to 8 iterations, 7 or 8 or more, because it was taking 4 days to train for the 6 iterations, so we didn't have time to go past that. That'd be a great area for future investigation. Couple quick references. That's all. Take questions and I'll show a demo video here for some results. There we go. So if you think about the augmented reality use case, the goal in augmented reality is sort of to trick the human visual system into having a seamless experience, which is very difficult because of how sensitive the human visual system is. So shown in the video here, we have initial course poses that are passed to our network on the left and our predictions of the refined pose on the right. Note the high levels of occlusion in this scenario here. This is sort of a long video, so I'm going to skip ahead. This is on the coffee can object. Oops. Doesn't like my double click. Here we go. This is a different object, the sugar box. We had pretty good results on both of these objects. Some of the objects that are more difficult to deal with are ones containing symmetries. There's a whole set of reasons for that that I won't talk about. Doesn't like me skipping forward. I'll leave it at that. Any questions?
For the talk. So we did this level insight that the states in LSTM should ensure that they are over iterations, you always get better.
Correct.
But would this force you to get stuck in local minimums? For example, if you were saying initialize the object with this 180-degree flip.
Right.
Now if you do render and compare and try to rotate it, the error will increase until it goes down when it's flipped over. But if you enforce that, okay, it has to improve over subsequent iterations, it would never be able to flip 180 degrees.
Great idea, and that was an idea I had, is how to add some additional constraints on the refinement process, how to know when to stop, how to know when we're doing better or worse. Absolutely. That great idea for something else to look into. Yep. All right, thanks everybody.
Great, no other questions, thanks again. And let's move on. The next one, the
Last, not the last, no. Almost the last. Yeah. Okay, we have one remote video and one in person. Is G-Sen here? The person? Yeah. And then we'll play the video and yeah, we'll wrap it up. Which one? CVPR 23? Yeah. Yeah, okay. And which one? Yeah, it works. You should go. Zoom. Opening. Okay. It works. And you present slideshow. Play from start. Yeah. You have the presenter notes here.
Oh, everyone, yeah, good to be the last. Yeah, we are presenting this pre-trained pixel-aligned reference network for 3D human reconstruction from a single view image. And this is work done by me and two of my students in the middle and on the right. And the contents of this talk, we have 4 parts. Yeah, first of all, I would like to point out the issues, and then our approaches, and then the experiments for performance evaluation, and then a conclusion. And this is a comparison of our reconstructed human faces samples with all other state-of-the-arts. It's hard to see, yeah, probably without this small circles. As you can see that some local parts are reconstructed, results not as good as the ground truths. Even ours, the forearm reconstructed is not that good in terms of the posture of the arm, the shape of the arms, and not to mention, for example, the one made by Icon 2 here. The hand is actually off the mouth. So that's the one of the issue we would like to address in this work, the accuracy in the reconstructed body parts. And the other issues we would like to address is the time-consuming training. Yeah, later on in our performance comparison, we will show you how we save time in terms of the training as well as the inference time, because if we are using a pre-trained model as a reference, so that we have a better initial condition to begin with, instead of just build the whole 3D human body all from scratch. Okay, here highlights the differences between our approach and others. Yeah, we probably is the first model that considers pre-trained model. Yeah, all this pre-trained model provided by, for example, PIFU, PIFU HD, Icon, and Hamir, all came up in this in the last few years. And we put this pre-trained model in our pipeline, and they use the pre-trained model as the initial condition to initial shape, and to make up the errors, the errors between the pre-trained model and the ground truth. And through training, we will make our model better focus on those small parts, on those local parts, yeah, which shows large error between the model, the pre-trained model, and the ground truth. And we also present this improved dual path architecture. Yeah, later I will focus. I will give more details on that part. And also, we will be able to reduce the hardware requirements for high resolution reconstruction. And most of our work focus by using PIFU, the pixel aligned model for the pre-train. So this is the the first part of our architecture, we have an input image, 2-dimensional, one single view. And we use that to generate a pre-trained model by using for example, a trained model already there available off the shelf. For example, you can assume this is a PFU or icon. Most of our study just focus on using PFU. And the input image allows us to do this image-to-image translation so that we will be able to get a front view normal and a back view normal. And the pre-trained model also allows us to get the normals from 4 views, from back and the 2 sides. So we have actually 6 normal views for the reconstruction. Yeah, 2 from image-to-image translation and 4 from the pre-trained model. And our architecture is built on 2 path encoders. One of them is made by stack hourglass, and the other one is made on UNet. We denote one of them by H1, the other one H2, and we call the whole thing 2-path architecture. And the outputs from actually the feature encoding from the 2-path feed 1 and the feed 2. I didn't put in the that's a feed 1 and feed 2. And the feed 1 and feed 2 consists of 2 feature vectors, and all these feature vectors will be concatenated and together with the spatial information Vx, Vz, and Dz here. In these 3 spatial coordinates. All these are from the pre-trained model. So the pre-trained model actually met the spatial information of each pixel available that way. So we put this all concatenated together and then drive the multi-layer perception MLP, and as the dimension in here, and we denote the whole MLP as G. And then just using the Marching cube to find to locate the 3D mesh in terms of the whole 3D shape. And this is the just for your reference, this is a review of the PFU architecture. They use 2-path architecture, but one of the paths is to reconstruct the 3D mesh, and the other one is to recover the texture. And we use 2-path architecture solely for reconstruction of the 3D mesh. We ignore the texture part, and we only compare the result for the 3D mesh. And you can see that from these single cases that in terms of the close texture, ours is much better than PFU. PFU seems to be without the high frequency details. And you go through our reconstructed surfaces, you can see the textures, you can see the folds along the clothes. And yeah, later on I will enter the experimental part, and our comparison and our study, all the model were trained and retrained on the same settings. And the training set is actually from the T-human data set, and the evaluation data set is from random people. And we arbitrarily selected 45 scans for evaluation. And this is an ablation study on the 2-pass encoders. Yeah, if we are using the H1 and H2 as proposed, yeah, that's the result, and we can compare the reconstructed. If we only use H1 or H1, or both paths are using H1, and the reconstructed limbs are not as good as ours. And this is the, it will reverse the order. Yeah, if the upper path, we use UNet, the lower path, we use the hourglass, then the depth reconstruction is not that good. And this happens in all these cases as we see it in our experiments. And in terms of the quantitative comparison, instead of, in addition to this 2-path architecture comparisons, different settings, and the special coordinates inputs, and we also compare the Gaussian perturbation with different standard deviations. And in addition to all this, we compare our performance with with different picture model, and we have tested 3 picture model. One is PFU, and the other PFU HD, and SPML-X, all released recently. And it shows that our approach is better with PFU, so it can deliver the lowest shampoo distance as well as P2S distance differences. Okay, after this one, this is a qualitative comparison with different picture model. And this is a quantitative comparison. In terms of numbers, ours again performs best with PFU as the picture model, and the inference time we can reduce to 14 seconds, and the training time 2 hours and 30 minutes just for one single epoch. And to train the whole thing, at least we know we have to have 200 to 250 for whole thing to converge. But in our way, we already see the advantage of by using picture model, because we can better constrain the initial model, the initial search for the right position in the 3D mesh. And this is the comparison with in terms of the error, the surface reconstructed errors between the reconstructed model and the ground truth. And the one at the bottom shows that if our model with PFU, it seems to be that the reconstructed surface can be can be good in terms of the overall quality as well as the local components. Yeah. And yeah, the particular part, the special part of our approach is that we consider, probably the first model consider the trend model is a pre-trained model so that we can better constrain the search in the query process as to where to locate the surface point in the 3D searching cube. And yeah, this is the way that we can build a better mesh surface, and shows that this is also shows that in our experiments. All right, this is probably the end of my presentation. Any questions?
Okay, since there are no other questions, let's thank our next panel speaker. And then we'll play the video for the last paper. And thank you all for participating both in the challenge and the workshop, presenting your work and coming here in person. We are very happy to see you, and I guess we will follow up at the website with the recording, maybe some slides, and the winners will get their prize. We will communicate with them, and we'll get the prize in the upcoming days. So thanks, and I'll play the last video.
Hello, my name is Nick, and I will be presenting our work with general robust and aligned behavior of the image. In this work, we focus on the problem of speaking and human vision data. Using data and human parameters for the image size of the physical and simple interpretation of safety, the goal is to find the parameters of the data to start the human vision for the safety cycle. Earlier, the method of training is to be and to find the solution to the safety process. By iterating optimizing the volume of the parameters position. Similar would show that strong cloud functionality is driven by the distribution, which is representing the data driven for the cloud. Noticing the training the estimates, relying on deep learning based on the physical data function evaluating the physical data. There are two dominant classes of approaches. Migration based on the theory, but try to remove the balance between state and forward estimation as well as simplification. And the leadership is a part of the estimate goes closer to the middle of the training sequence. As user operations are having online, model variants to authentic information to improve performance, but frequently just goes closer to the middle. The availability of volume measurement opens up another skills verification, but that attempts to not improve false estimation performance in software with respect to pixel line. There are also interesting variations like the NDC model or just one model adaptation, but instead of two models being done with it. But again, these are only focused on forward performance improvement. Everything these balance support that performance rate, takes its current criteria. In this work, we present the public information to understand people, but tries to do balance of the work. We follow the habit of different and optimize approach using regression to obtain a visual estimate that is subsequently refined using different single direction cells to obtain the resulting human value. To achieve the vast general efficient performance, the direct range temporarily value difference. The relevant to the two conventional implementation step that is treated as a reduction of specific visibility points to successfully improve the human distribution information. The vastness is a figure of having to keep the loop, but strongly regular analysis is going to be. For the latter, we introduce the after adaptation of superstructure balance performance between four states and pixel lines. The third one is the introduction of the systems. Both flagship approaches require mapping between the body model joints and the key points connected to the physical in a body model. However, not the mapping for artificial performance. But take for example the picture of the body model and the picture of the by the some prior works have chosen to not use the others in the body model is less better than but none of them will never go and differences in the approach as we love to do at the same time. Another reason that can learn to request for specific dates, a process of suffering from insufficient visualization with joint estimating close to the surface. Instead, we look between the corresponding to the specific image and parameterize the joint position using the barocentric coordinate formed by two approximately moving joints. Using physical performance having the data of higher quality correspondence, we can perform high aspect parameter shifts to the bison, resulting in good uptake of the joint liquids. As these joints are growing within the market frame, they are increasing importance for the body and safer life. We need to improve the good performance. Apart from the improved total validation, we also observe a variety of higher quality pixel parameters. Indicating that prior work is included in people concerns with traffic and the objective methods. Our second limitation concerns victimization of data. Typically, the state and both parameters are controlled by the equation parameter. We introduce a state where the parameter factors for the body and state are kept separate, and we tend to update them jointly to update them terms, keeping the other parameter factor fixed, similar to the coordinate. This leads to improved optimization of the minimized state, especially in situations where people need to look at the changes. For our final adaptation and condition of the negative frequency, we are from the studio to gain time mathematics. From this studio, we discuss the linear and after frequency video and traffic simulations that can be combined into an interesting frequency. This is using the boundary matching term after tracking the studio boundary and using the sample efficiency. However, this will result in artifactual objective and considered floating. To overcome this, we introduce asymmetry by downscaling the energy system. This will happen to floating, allowing the body to not shift to match the boundary, but instead of simulating twice to analyze the overshoot. And having any certain contrary the symmetric value, their assessments tend to the natural and closing surface. Overall, the day body taking framework type is offering a good balance between force and safe in the adoption of the pixel. Compared to other optimization-based approaches and reduce uptake due to the higher quality correspondence in safe specific character. While data visualization models are perfect as a distribution function, and the good force and pixel quality even for target perspectives. When data simulation performance is specifically modeled, if only improve performance in that result, validation without sacrificing quality, and we can also better handle output functions. Accordingly, we will estimate the state of human challenge, stakeholder integration. Our framework is about to reflect. The table framework completes parts of the machine that pass. My started approach to line is in a very version. There have been models for two bodies in mathematics and namely version. To overcome the software diagram is something about it.
I guess that although we faced some technical issues with the last talk, it's finished. And yeah, if there are any questions towards the authors, let's see if anyone is on Zoom. There are 10 people. Yeah, the author is on, seems to be on Zoom. If anyone wants to answer anything, but anyway, we are already over time, so I think we have to close it here because the other workshops are starting at 1:30 and 2, so we might have time for a question, but not much more. Are there any questions? So if there are no questions, let's thank everybody that you came here today to participate in the workshop. Thank all the participants in our challenges. Unfortunately, a lot of them didn't make it here, so I get 3 spare certificates, but we thank them and we thank all the participants and the speakers for the nice talk, although most of them have left. So thank you everybody. And we hope next year we organize again the workshop. Thanks also Xi and Shanghui who weren't able to come. I think Shanghui is on Zoom. She's not. She's there. Okay, yeah, they weren't able to come, unfortunately, due to visa issues. But thank you, and thank Kaitun also, who helped organize the workshop, and Bharat, who was being here all day with me, and this one who is not here now, and Gerard. Okay, thanks everyone from the organizing committee and the participants, and yeah, have a nice rest of the day.